There is a fortress in Syria that has guarded a mountain pass for 800 years. Its walls have faced Mongol hordes, crusading armies, and the relentless erosion of centuries, yet they stand unbroken. If you were to press your ear against its ancient stones, some say you could almost hear the echoes of a forgotten genius, the subtle hum of engineering principles so advanced that we are only now beginning to understand their full brilliance. This is not a relic of a primitive past. It is a testament to a school of engineering so sophisticated that modern architects and structural engineers from the world's top firms still travel to these sites, note-takers in hand, to study what these master builders achieved without the aid of computers, calculus, or modern materials. These were the hidden engineering feats of the knightly orders, and their secrets have been waiting in plain sight for us to rediscover. Picture the Knights Templar, not just as warriors in white mantles, but as visionary builders whose concentric castles redefined the very concept of defense. Imagine the Teutonic Knights executing hydraulic engineering projects that would challenge modern urban planners. Envision the Hospitallers designing infirmaries with passive temperature control systems that maintained perfect climates in desert heat and alpine cold. These warrior monks were more than soldiers of faith. They were the civil engineers, the architects, and the unsung physicists of their age. They operated in a world of profound limitations, yet they produced innovations in masonry, acoustics, and sustainable design that we struggle to replicate with all our technological might. Their blueprints, encoded in stone and mortar, contain answers to problems we are still grappling with today, from how to build resilient cities to how to create structures that exist in harmony with their environment. So why does this ancient knowledge matter to us now? Because we are living in a time where we are rediscovering the value of sustainability, of resilience, and of building things to last for generations, not just for decades. The knightly orders built for eternity, and their legacy offers us a treasure trove of insights that feel startlingly urgent. In this video, we will embark on a grand tour of 25 of their most astonishing hidden engineering marvels. We will decode the silent language of their architecture, from cryptographic symbols woven into chapel walls to psychological warfare principles built into fortress layouts. We will see how their understanding of natural forces created buildings that were alive, responsive, and deeply intelligent. This is a journey into the mind of the medieval master builder, an exploration of a lost world of innovation that continues to quietly shape our own. The stones are ready to speak. All we have to do is listen. To truly grasp the revolutionary nature of these engineering feats, we need to step back into the tumultuous world of the Crusades. This was not merely a period of conflict, it was a vast, if violent, crossroads of civilizations. For the first time, European knights arriving in the Near East found themselves confronting architectural and engineering traditions that were centuries more advanced than their own. They marched from castles of wood and earth to stand before the towering stone fortifications of Byzantine cities and the sophisticated hydraulic systems of Islamic palaces. This confrontation was a shock to the system, but for the military orders like the Templars and Hospitallers, it became an unparalleled learning opportunity. These warrior monks were not just soldiers, they were pragmatic institution builders. They possessed the unique capacity to observe, analyze, and most importantly, adapt the superior techniques they encountered. They saw how Islamic architects used pointed arches to distribute weight more efficiently, allowing for taller, more graceful structures. They studied Byzantine concentric wall designs that created deadly killing zones for attackers. And they recognized the life-saving importance of the intricate canals, the underground water channels that sustained cities in arid climates. This knowledge wasn't just admired, it was systematically reverse-engineered and fused with European building practices to serve their own unprecedented needs. What made the knightly orders uniquely positioned to capitalize on this knowledge was their extraordinary organizational structure. Think of them not as loose collections of knights, but as the first truly multinational corporations with a centralized command, vast financial resources, and a relentless drive for standardization. While a local baron might build a single castle using the tried and true methods of his forefathers, the Templars or the Teutonic Knights were managing simultaneous construction projects across thousands of miles, from the sun-baked hills of Palestine to the frozen plains of Prussia. This scale demanded innovation and efficiency. They maintained detailed archives of their building techniques, creating what we might now call a corporate knowledge base. A master mason working on a Templar commandery in France could send a letter to a brother in charge of a fortress in the Holy Land, sharing a solution for a particular structural challenge or a new method for fortifying a gatehouse. This continuous cross-pollination of ideas created a feedback loop of engineering improvement that was unheard of in the fragmented feudal world. Their network of preceptories and commanderies functioned as a living laboratory, where successful innovations could be rapidly tested, refined, and deployed across an entire empire of stone. Furthermore, their dual identity as both monks and warriors infused their architecture with a profound sense of purpose that went beyond mere utility. A Cistercian monastery might prioritize spiritual asceticism, and a royal castle might focus solely on raw military power, but the knightly orders had to seamlessly blend both. Their churches needed to be places of deep contemplation and divine majesty, while their fortresses had to be impervious engines of war. This unique requirement forced them to become masters of architectural synthesis. A single Templar chapel, for instance, wasn't just a place of worship. Its acoustics were engineered to enhance the solemnity of their rituals. Its layout was designed to control the movement of initiates, and its foundations were often strong enough to serve as a last redoubt during a siege. This marriage of the spiritual and the martial, of symbolic meaning and brutal pragmatism, resulted in a unique architectural language. It was a language written in stone, speaking of both heavenly devotion and earthly power. And it is this rich, complex context that explains why their buildings were not just strong, but truly, enduringly brilliant. Now, let's turn our attention to the first and perhaps most iconic of these hidden feats, the Templars' revolutionary concentric castle design. Before this innovation, a typical castle was a formidable structure, certainly, but it often relied on a single, mighty curtain wall. An attacker who managed to breach that one barrier, perhaps by sapping a corner or overwhelming a gatehouse, could essentially flood the courtyard and bring the defense to a swift and brutal conclusion. The Templars, drawing from Byzantine and Islamic military architecture they encountered in the Holy Land, fundamentally rethought this entire defensive paradigm. They asked a simple but profound question: what if a castle didn't have just one line of defense but several? The result was the Concentric Castle, a masterpiece of layered protection that turned the entire concept of a siege into a nightmare for any attacking force. Imagine yourself as a soldier storming a castle like the famous Crac des Chevaliers, a Templar stronghold that still stands as a textbook example of this design. You and your comrades have just sacrificed dozens of men to break through the massive outer wall, perhaps by battering down a gate or collapsing a section of stone. Instead of finding the open courtyard you expected, you burst into a narrow, stone-lined corridor, a killing zone. You are now trapped in a carefully engineered space between the outer wall you just breached and a second, even higher inner wall that looms above you. From your position, there is no cover. Archers on the inner wall are shooting down at you from 3 sides, their arrows finding easy targets in the cramped, chaotic space. Meanwhile, soldiers on the outer wall, which you thought you had conquered, are now behind you, pouring boiling oil or dropping heavy stones on your head from machicolations, those projecting galleries with holes in the floor. There is nowhere to run. Advancing means confronting another, even stronger gatehouse, while retreating means going back through the breached outer wall under a constant hail of projectiles. This was the genius of the concentric design. It didn't just stop an attack, it systematically dismantled it layer by layer, demoralizing the attackers and maximizing casualties at every step. The psychological dimension of this architecture was as calculated as its physical structure. The very sight of these concentric rings of walls created a sense of daunting, almost impossible scale for a besieging army. It communicated a clear message. Breaching the first wall was not a victory, but merely the first step into a carefully prepared death trap. This played on the natural fear and confusion of soldiers, who would have expected a single, decisive push to win the day. Instead, they were faced with a seemingly endless series of obstacles, each more dangerous than the last. The design forced attackers into predictable, funneled paths where defenders could concentrate their fire, turning the chaotic randomness of battle into a controlled, systematic defense. It was a form of architectural warfare that targeted the mind as much as the body, breaking the will of an enemy long before their ranks were completely destroyed. The legacy of this thinking is astonishingly alive today. Modern security architects and urban planners study these concentric principles when designing everything from secure data centers to airport perimeters, and even the protection of critical government facilities. The concept is known as defense in depth. Just like the Templar castles, a modern high-security site doesn't rely on a single fence or a lone guard post. Instead, you'll find a series of progressively more secure rings. An outer perimeter might be a simple fence with motion sensors, anyone bypassing that would then encounter a patrolled area, then a stronger physical barrier, then biometric access controls, and so on. Each layer is designed to delay, detect, and deter an intruder, buying time for a response force and making a successful breach exponentially more difficult. The fundamental principle is identical to that of crack des Chevaliers: never present a single point of failure. The Templars' understanding of spatial control and progressive defensive rings, achieved with nothing but stone, timber, and strategic genius, continues to provide the foundational blueprint for how we protect our most valuable assets in the 21st century. But the Knightly Order's genius wasn't limited to grand defensive schemes. It extended right down to the very stones they laid. While the Templars were perfecting castle design, the Hospitallers were achieving something that, to the untrained eye, borders on magic. They mastered advanced masonry techniques that allowed them to construct vast, soaring structures with an almost supernatural precision. Walk into one of their great halls or chapels, and you might not immediately notice what's missing. The walls are seamless, the arches are flawless curves of stone. There are no thick, obvious mortar lines holding everything together. That is the heart of their secret. They built with such incredible accuracy that the stones themselves, cut with complex, puzzle-like joints, locked together under their own weight, creating self-supporting masterpieces that have defied time and nature in ways modern buildings often cannot. The secret lay in a profound understanding of geometry and physics. Each stone block was not a simple rectangle. It was a uniquely shaped piece of a three-dimensional jigsaw puzzle. The Hospitallers used complex interlocking joints, dovetails, mortise and tenon, and other intricate cuts that were carved with painstaking care. When assembled, these stones couldn't slide or shift. They transferred weight and force along optimal paths, channeling the immense gravitational loads down through the structure in a continuous flow. An arch wasn't just a row of wedged-shaped stones. It was a single, coherent structural entity where every piece pressed against its neighbors, creating a stable equilibrium that could support astonishing weights. They were essentially creating monolithic structures from thousands of individually placed stones, a technique that gave their buildings a unique resilience. Modern technology has finally allowed us to peer into the heart of this ancient genius. Using high-precision laser scanning and ground-penetrating radar, engineers have mapped these stone connections to within a millimeter. What they've discovered is breathtaking. The tolerances achieved by these medieval masons are often finer than what we see in many contemporary concrete constructions. The surfaces are so perfectly matched that in many places the thin layer of lime mortar used was almost superfluous, acting more as a lubricant during construction and a weather seal than a true binding agent. This precision is precisely why these structures have survived centuries of earthquakes that have reduced modern reinforced concrete buildings to rubble. A rigid, monolithic concrete structure can crack and fail when the ground shakes, but the Hospitaller's interlocking stonework has a slight, built-in flexibility. The stones can minutely shift and settle against each other, absorbing and dissipating seismic energy without collapsing. They move with the earthquake rather than fighting against it, and then settle back into their perfectly engineered positions. This ancient wisdom is now inspiring a revolution in sustainable and seismic-resistant architecture. Contemporary architects and engineers, particularly in earthquake-prone regions like Japan, Peru, and California, are actively studying and adapting these Hospitaller techniques. The goal is to reduce our overwhelming reliance on cement, a material whose production is one of the largest single sources of global carbon dioxide emissions, and on steel reinforcements, which are energy-intensive to manufacture. By designing modern buildings with precisely engineered, dry-stacked or minimally mortared stone elements, we can create structures with a far lower carbon footprint. These buildings would be naturally cool in summer and warm in winter thanks to the thermal mass of stone, and they would possess an inherent resilience to seismic activity. It is a powerful convergence of ancient insight and modern necessity, proving that the Hospitaller's stone cutting yards were, in fact, laboratories for a form of sustainable engineering that our planet desperately needs today. The fact that they accomplished this with nothing more than chisels, plumb bobs, and a deep, intuitive grasp of mathematics remains one of the most humbling and inspiring puzzles in the entire history of construction. While the Hospitallers were mastering the silent language of stone, another knightly order was solving a problem even more fundamental to survival: the secret of water. In the harsh, contested landscapes of Prussia and the Baltic, where the Teutonic Knights carved out their state, a reliable water supply wasn't just a matter of comfort. It was the absolute determinant between a fortress holding out for a year or falling in a week. A besieging army's primary strategy was always to poison wells or cut off access to rivers, waiting for thirst to do its grim work. The Teutonic Knights responded to this threat with one of the most brilliantly holistic engineering solutions of the Middle Ages: hidden water conduit systems that turned their castles into self-sufficient hydrological fortresses. These were not simple wells. They were sophisticated underground networks, marvels of low-tech hydraulic engineering that functioned like the circulatory system of a living organism, bringing life in and keeping death out. The genius of these systems lay in their multi-layered design. Deep beneath the castle courtyards, the knights and their engineers constructed elaborate networks of tunnels and channels that tapped into underground springs or distant, concealed water sources. But they didn't just channel water, they managed it with astonishing sophistication. The systems often began with natural filtration chambers, where water was passed through layers of sand, gravel, and charcoal to remove sediment and impurities, providing a clean supply long before the science of germs was understood. From there, the water was guided through a gravity-fed network that used subtle changes in elevation and pipe diameter to regulate pressure, ensuring a steady, controllable flow to various points within the fortress: the kitchens, the infirmaries, the stables, and most crucially, hidden cisterns deep within the innermost keep. Perhaps the most clever feature was the incorporation of secret access points. These were carefully camouflaged openings, often located in a basement storeroom or even within the chapel itself, allowing defenders to draw water without exposing themselves to enemy missiles. A besieging army camped outside would see a silent, seemingly parched castle, completely unaware that deep below their feet, fresh, clean water was still flowing, sustaining the defenders and sealing their own fate. This medieval understanding of hydrology and geology is what gives these systems their enduring power. The Teutonic Knights possessed an intuitive, yet remarkably accurate, grasp of the water table and underground geology. They knew how to identify and tap into artesian springs, those that flow to the surface naturally under their own pressure, and how to construct canal-like tunnels to gently guide water from distant sources over miles without a single pump. They built their conduits from carefully selected, durable materials like hollowed-out logs, fired clay pipes, and sometimes even lead, all designed to last for generations. The proof of their success is written in the ruins themselves. Many of these systems remained fully operational for 500 years or more, outlasting the Knights' own state and continuing to function through wars and upheavals, a silent testament to an engineering philosophy built for permanence. Today, the principles embedded in these ancient water networks are experiencing a dramatic resurgence. Modern urban planners and disaster preparedness experts study the Teutonic systems not as historical curiosities, but as viable models for 21st century water security. In an era of increasing climate instability, where hurricanes, earthquakes, or cyber attacks can cripple a city's electrical grid and shut down its modern pumping stations, the value of a passive, gravity-fed water system becomes incalculable. The Knights' designs inform contemporary plans for redundant municipal water supplies, showing how cities can create backup networks that function independently of power. Furthermore, their holistic approach from source protection to filtration to secure distribution is a cornerstone of modern sustainable water management in developing nations. Engineers working in arid regions now apply these very same gravity-fed and naturally filtered channel techniques to bring clean water to rural villages, proving that a 700-year-old solution can be more appropriate and sustainable than complex, expensive, and energy-intensive modern technology. The Teutonic Knights, in their quest to survive a siege, accidentally engineered a blueprint for water resilience that our modern world is only now rediscovering as an essential key to our own future. Now let's step out of the fortress and into the chapel, where the Templars performed a different kind of magic, one of sound. In their most sacred spaces, they achieved acoustic phenomena that seemed to defy logic. Picture a long stone chapel on a windy day. Outside, a storm might be raging, but within, there is a profound, almost unnerving silence. Yet, if the priest at the far altar were to whisper a prayer, that soft, breathy sound would travel the entire length of the hall and arrive at your ear in the back row with crystal clarity, as if he were standing right beside you. This was not a mystical miracle, it was engineered. the Templars, through an intuitive mastery of physics, had transformed their chapels into sophisticated instruments for the human voice, creating an auditory experience that reinforced their spiritual authority and deepened the mystery of their rituals. How did they accomplish this without a single decibel meter or sound wave simulation? The secret lay in the deliberate sculpting of space and material. Every surface in a Templar chapel was an active component in an acoustic system. The soaring, barrel-vaulted ceilings weren't just for grandeur. Their specific curvature was calculated to act as a sound waveguide, channeling spoken words along its length while preventing the sound from dissipating upwards. The stone itself was carefully selected and finished. Rough, porous stone can absorb sound, but the polished marble and hard limestone used on key interior surfaces were chosen for their reflective properties. Even the placement of pillars and the geometry of the arches played a role. They were positioned not just to hold up the roof, but to break up and diffuse sound waves in a way that prevented muddy echoes, ensuring that speech remained intelligible rather than becoming a reverberant cacophony. This holistic approach meant that the architecture itself was filtering and focusing sound, amplifying the frequencies of the human voice while simultaneously dampening the low rumble of wind and the clatter of hooves from outside. It was a form of architectural noise cancellation, centuries before the concept existed. The modern world is only just catching up to the sophistication of this medieval acoustic engineering. Today, when architects design a world-class concert hall, they face the exact same challenge the Templars did: how to make unamplified sound carry perfectly to every single listener. The solutions they've developed through complex computer modeling bear a striking resemblance to those ancient chapels. The undulating ceilings of many modern performance spaces, for instance, function much like those Gothic vaults, breaking up sound waves to create a rich, full ambience. The strategic use of reflective and absorptive materials to control reverberation time is a direct parallel to the Templars' selection of stone and plaster. What these contemporary acoustic engineers have discovered is that the Templars had stumbled upon the fundamental principles of wave physics through trial and error and geometric intuition. They understood that sound is a physical force that interacts with its environment, and they learned to sculpt that environment to achieve a specific, powerful effect. This feat is perhaps the most poignant example of the knightly order's unique fusion of the practical and the spiritual. The acoustic design of a Templar chapel served multiple, overlapping purposes. On a purely functional level, it ensured that every initiate, even one standing at the very back of a dimly lit hall, could hear and understand the sacred rites and secret instructions. This was crucial for maintaining the order's discipline and secrecy, but on a deeper, psychological level, the acoustic environment they created was a profound tool of immersion. When a whisper can traverse a vast space untouched, it feels supernatural. It transforms a mundane message into a divine revelation, heightening the sense of awe and mystery that surrounded the Templars. The very architecture was preaching a sermon about the power and presence of the divine, a sermon heard not just with the ears but felt in the bones. This seamless integration of audiological science with spiritual theater demonstrates a level of holistic design thinking that modern architects still strive for when creating spaces meant to move the human spirit. From the silent symphony of Templar acoustics, we move to a different kind of environmental mastery, one that dealt not with sound waves but with the very air itself. In their role as healers, the Knights Hospitaller faced a medical challenge as demanding as any siege: how to create the perfect environment for recovery. A wounded knight, racked with fever in a sweltering Palestinian summer or shivering in the damp cold of a Rhodian winter, had little chance of survival without a stable, temperate space. Their solution was not to fight nature with force, but to collaborate with it, developing passive temperature regulation systems within their infirmaries that created consistently comfortable conditions using nothing but stone, air, and celestial geometry. These were not just rooms, they were carefully tuned instruments for healing, microclimates engineered with a sophistication that makes our modern reliance on furnaces and air conditioners seem almost clumsy by comparison. The genius of these systems lay in their multi-layered approach, a harmony of three core principles working in concert. First was strategic orientation. Before a single stone was laid, Hospitaller architects would spend months observing the sun's path across the sky at different times of year. They positioned their infirmary buildings so that the long, windowed facades faced precisely south in the northern hemisphere. This meant that during the short, cold days of winter, the low-hanging sun would stream deep into the rooms, its rays absorbed by the stone floors and walls, naturally warming the space. Conversely, during the blazing summer, when the sun rode high overhead, the deep overhanging eaves of the roof, calculated with remarkable precision, would cast the interior into shade, blocking the intense heat while still allowing indirect light to illuminate the space. This was solar geometry in its purest form, a built-in seasonal thermostat that required no moving parts. The second principle was the masterful use of thermal mass. The Hospitallers built their infirmaries with massively thick walls and vaulted ceilings made of dense limestone or sandstone. To a modern visitor, these might just feel solid and imposing, but they were actually performing a critical function. These materials have a high capacity to absorb and store heat energy. During the day, the sun-warmed stone would slowly soak up warmth, preventing the interior from becoming too hot. Then, as the temperature dropped at night, the stone would gradually release that stored heat back into the room, moderating the chill. In the summer, the same mass worked in reverse, staying cool during the day and slowly absorbing the heat from the air inside. This created a natural thermal flywheel effect, smoothing out the sharp peaks and valleys of daily temperature swings and maintaining a remarkably stable, gentle climate that was neither too hot nor too cold for a vulnerable patient. It was a form of architectural inertia, using the building itself as a giant, passive battery for thermal energy. The third, and perhaps most clever, element was the integration of clever air circulation channels. The Hospitallers understood that stagnant air is unhealthy air, and that strategic ventilation was key to both comfort and hygiene. They engineered this not with fans but with physics. They incorporated what we now call a stack effect or thermal chimney system. Strategically placed vents low on the cooler, north side of the building would draw in fresh air. This air would then be warmed by the patients and the interior environment, causing it to rise. At the highest point of the vaulted ceiling, carefully designed openings would allow this warmer, stale air to escape, creating a constant, gentle, and draft-free circulation that flushed out humidity and odors while bringing in a steady supply of fresh oxygen. Sometimes these ventilation shafts were even routed through the massive walls themselves, allowing the incoming air to be pre-cooled by the stone in the summer or pre-warmed in the winter before it ever reached a patient's bedside. This was climate control at its most elegant and efficient. Today, the principles perfected in these medieval infirmaries form the very foundation of the modern passive house movement. Architects and engineers striving for net-zero energy buildings are essentially relearning what the Hospitallers knew by instinct: the precise solar orientation, the strategic use of thermal mass in materials like rammed earth or concrete, and the design for natural cross-ventilation are all standard practices in high-performance sustainable design. What is humbling for modern engineers is the realization that despite our advanced materials and complex energy modeling software, we often struggle to achieve the same level of year-round comfort with zero energy input that the Hospitallers accomplished routinely. Our modern glass and steel buildings, with their thin skins, often become uninhabitable ovens or freezers without the constant, energy-guzzling hum of mechanical systems. The Knights' buildings, by contrast, were inherently resilient, their comfort guaranteed by the laws of physics embedded in their design, not by the fragile supply of electricity. This ancient approach offers a powerful and urgent lesson for our current climate challenges. In a world grappling with the carbon emissions of heating and cooling buildings, the Hospitaller model presents a path toward radical efficiency. By designing with nature rather than against it, we can create structures that require a fraction of the energy, reducing both their environmental impact and their operating costs. Their work demonstrates that true sustainability isn't necessarily about adding more complex technology, but about thinking more intelligently from the very beginning. It's about remembering that the sun, the wind, and the earth itself are powerful allies in our quest for comfort, if only we have the wisdom to design for their rhythms. The Hospitaller infirmaries stand as a timeless testament to this philosophy, proving that the most advanced environmental system might not be a machine we install, but a building we thoughtfully conceive. While the Hospitallers were engineering spaces of quiet healing, other members of the knightly orders were perfecting the art of delivering catastrophic force at a distance. Picture the scene outside a defiant castle. After weeks of stalemate, a monstrous wooden frame begins to rise in the besiegers' camp. It's a counterweight trebuchet, the ultimate expression of medieval artillery, a machine so powerful it could change the outcome of a siege in a single, earth-shattering strike. The knightly orders, particularly the Templars and Teutonic Knights, didn't just use these weapons, they refined them into instruments of terrifying precision. Their most advanced machines could launch a stone projectile weighing as much as 300 pounds across a distance greater than 3 football fields, and with an accuracy that could target a specific section of a fortress wall repeatedly, methodically pounding it into rubble. This was not crude hurling, it was the applied physics of gravity and leverage engineered on a colossal scale. The true genius of these machines lay in their sophisticated mechanical balance. At its heart, a trebuchet is a giant lever. A very long throwing arm is pivoted off-center with a massive weight box, often filled with tons of earth and stone, attached to the short end, and a sling holding the projectile at the long end. The knightly engineers became masters of tuning this system. They understood that the ratio between the length of the short arm and the long arm was the key to maximizing power. But their innovations went far beyond this basic principle. They perfected the weight distribution within the counterweight box itself, designing it so the weight would shift and fall in a way that optimized the transfer of energy, creating a smooth, powerful acceleration rather than a jarring jerk that could shatter the machine. The release mechanism was another masterpiece of practical engineering. The sling was attached with a cunning hook that would release the projectile at the perfect point in the arc too early, and the stone would fly harmlessly high into the air too late, and it would slam into the ground just in front of the machine. Getting this timing exact with nothing but wood and rope required an intuitive grasp of rotational dynamics that we would now calculate with advanced computer simulations. Furthermore, the structural bracing of these trebuchets demonstrated a profound understanding of material strength and load management. The entire framework had to withstand not only the immense dead weight of the counterweight, but also the violent recoil and shock of each launch. The knightly builders used complex systems of diagonal supports, tension ropes soaked in animal fat to keep them taut and strong, and mortise and tenon joints that allowed the structure to flex minutely without failing. Building one of these machines was a massive logistical and intellectual undertaking. It required felling and shaping enormous trees, transporting and assembling them under the threat of attack from the castle walls, and then conducting test shots to calibrate the machine's range and accuracy, all without a single textbook on physics or a modern engineering diagram. The master carpenter in charge of such a project was essentially a practical physicist, his knowledge passed down through an oral tradition of siegecraft, a living database of mechanical principles learned through centuries of trial and error, success and catastrophic failure. The legacy of this medieval mechanical genius is far from confined to history books. Modern military and aerospace engineers actively study the principles embedded in these trebuchets. Consider the catapult systems used to launch fighter jets from the short decks of aircraft carriers. The problem is remarkably similar: how to accelerate a massive object to a high velocity over a very short distance. While the power source is now steam or electromagnetic rather than gravity, the fundamental challenge of managing immense forces, achieving a smooth and precise acceleration curve, and releasing the payload at the exact right moment is directly analogous to the trebuchet engineer's art. The mathematical models used to design these modern catapults share a common ancestry with the intuitive calculations of the medieval siege master. Both seek to harness and control tremendous power with perfect timing. Beyond the battlefield, the principles of stored potential energy and controlled release pioneered by the trebuchet find application in life-saving technology. Emergency rescue equipment, such as certain types of line-throwing devices used by coast guards to fire ropes to ships in distress, operates on similar concepts of stored and suddenly released energy. Even the study of biomechanics, analyzing how athletes throw a javelin or a baseball, draws upon the same fundamental physics of levers, counterweights, and timing that these knightly engineers mastered in wood and stone. Their work demonstrates that the laws of physics are universal and timeless. Whether the goal is to breach a castle wall or launch a spacecraft, the principles of force, leverage, and energy transfer remain the same. The counterweight trebuchet stands as a monumental achievement of pre-Newtonian engineering, a testament to the power of the human mind to unlock the secrets of the physical world through observation, innovation, and the relentless drive to solve a problem, even if that problem was how to demolish a fortress from 300 yards away. While the thunder of trebuchets represented one kind of power, the Teutonic Knights were mastering another, far quieter form of strength, the power of systematic organization. In the vast, cold expanses of Prussia and the Baltic, they faced a challenge of speed and scale. Conquering territory from pagan tribes was one thing, holding it was another. To secure their gains, they needed to establish a network of fortified outposts or commanderies faster than their enemies could rally and counterattack. The solution they pioneered was as revolutionary as it was simple: modular construction. Imagine a medieval building site not as a chaotic scramble of masons carving unique stones for months on end, but as an orderly assembly line. The Knights had perfected the art of prefabrication, creating a catalogue of standardized building components: window frames, door lintels, stair treads, even entire sections of wall, that could be produced in centralized workshops during the winter months, then shipped by barge and wagon to new construction sites when the campaigning season began. This system was a masterpiece of logistical foresight. In their main commanderies, skilled craftsmen would work in sheltered yards, producing these standardized elements in large batches. A window frame made in Marienburg would fit perfectly into a wall section assembled in Riga, hundreds of miles away. This meant that when a new site was selected, the labor force, often composed of local conscripts or lower-skilled laborers supervised by just a few knight brothers with architectural training, could begin work immediately. There was no need to wait for a master mason to arrive and take measurements. The foundation would be laid according to a standard plan, and the pre-cut stones and timbers would be unloaded and assembled like a giant, life-saving kit. A functional, defensible outpost could rise from the wilderness in a matter of weeks, not years. This incredible speed allowed the Teutonic Order to solidify its control over newly conquered lands with breathtaking efficiency, creating a defensive web that could strangle rebellions before they even had a chance to spread. The fortress itself became a weapon of rapid deployment. The brilliance of this approach extended far beyond mere speed. It represented a fundamental shift in thinking about architecture, from one-of-a-kind artistry to systematic, replicable engineering. The Teutonic Knights were essentially running a medieval franchise operation, and every commandery was a branch office built from the same core blueprint. This standardization ensured a consistent level of defensive quality and architectural familiarity. A knight transferred from a commandery in Livonia to one in Pomerania would immediately know his way around the fortress layout, the location of the postern gates, the strengths and weaknesses of the defensive walls. This organizational intelligence, baked into the very stones of their buildings, created a formidable institutional resilience. It also allowed for incredible scalability. As the Order's wealth and territory grew, so too could its network of fortifications, all without overwhelming its limited pool of highly skilled architects and master masons. They had decoupled the act of design from the act of construction, a conceptual leap that would not become common in the building trades for another 600 years. Today, the ghost of the Teutonic Knights modular system lives on in some of the most urgent and forward-thinking areas of modern architecture. Contemporary architects examining their methods see a clear precursor to the entire prefabricated and modular construction industry. The principles are identical: design for manufacture and assembly, standardized components for quality and cost control, and separate the skilled fabrication process from the often less skilled on-site assembly. This is the exact philosophy behind everything from modern apartment buildings constructed from shipping container-like modules to the flat-pack housing systems being developed for rapidly growing urban populations. But the most poignant modern parallel is found in the field of disaster relief and humanitarian housing. After an earthquake, flood, or hurricane, the immediate need is for safe, dignified, and rapidly deployable shelter. Organizations like the United Nations and the Red Cross now employ modular, prefabricated building systems that can be air-dropped into disaster zones and assembled by local volunteers with minimal training, providing life-saving housing in days instead of months. The Teutonic Knights, in their drive to dominate a frontier, accidentally engineered a prototype for global humanitarian response. Their systematic approach offers a powerful lesson for tackling one of the 21st century's most pressing challenges: the global housing shortage. With billions of people needing adequate shelter, the traditional model of bespoke, on-site construction is simply too slow, too expensive, and too resource-intensive. The Knights demonstrated that standardization does not have to mean blandness or a loss of local identity. Their commanderies, while built from standardized parts, were often adapted to their specific locales, using local stone for foundations or adjusting roof pitches for heavier snow loads. This balance between core standardization and localized adaptation is precisely what modern architects are striving for with mass timber construction and panelized building systems. The Teutonic Knights proved that by thinking in systems rather than individual structures, it is possible to achieve a level of efficiency and scalability that can meet overwhelming demand. Their legacy is a reminder that sometimes the most profound architectural revolutions are not about designing a single beautiful building, but about designing a smarter way to build all buildings, a lesson as vital for addressing today's urban housing crises as it was for taming the medieval Baltic frontier. Moving beyond the physical realm of modular construction, we enter a far more subtle and mysterious dimension of knightly engineering, the art of embedding secret messages directly into the very fabric of their buildings. For these warrior monks, architecture was never merely about providing shelter or defense. It was a form of silent scripture, a way to encode their most profound spiritual and philosophical beliefs into stone. To an untrained eye, a Templar chapel might appear as a simple, if imposing, place of worship, but to an initiate, that same building was an open book, its pages written in the language of geometry, proportion, and celestial alignment. These cryptographic architectural elements transformed inert stone into a living repository of hidden knowledge, ensuring that their most guarded secrets would be preserved and communicated only to those deemed worthy of understanding. The primary tool for this architectural encryption was sacred geometry. The knightly orders were deeply steeped in the belief that God had created the universe according to mathematical principles, and that by replicating these perfect forms in their buildings, they were creating a microcosm of divine order on earth. The most famous of these principles was the golden ratio, a mathematical constant of approximately 1.618 that appears throughout nature, from the spiral of a nautilus shell to the arrangement of seeds in a sunflower. The Templars and others integrated this ratio with astonishing precision into the ground plans, elevations, and even the decorative details of their structures. The width of a nave might relate to its height by the golden ratio, or the placement of a key pillar might divide the space into these perfect proportions. This wasn't just an aesthetic choice, it was a theological statement. The building itself became a sermon on the inherent harmony of creation, a harmony that could only be perceived by those who knew how to look. Other geometric shapes held powerful symbolic meaning. The octagon, for instance, frequently seen in Templar chapels, represented the transition between the earthly square and the heavenly circle, symbolizing resurrection and regeneration. Every arch, every vault, every window was a piece of a larger geometric puzzle, its true significance hidden in plain sight. This encoding extended beyond static geometry to incorporate dynamic, celestial events. Many knightly structures were carefully aligned to function as sophisticated solar and lunar calendars. Specific windows or narrow apertures were positioned so that on the solstices or equinoxes, or on the feast days of particular saints, a single, brilliant shaft of sunlight would pierce the interior gloom and illuminate a specific point, perhaps a carving on the far wall, a particular flagstone on the floor, or the altar itself. This transient event, lasting only minutes, transformed the building from a static object into a cosmic clock. It connected the sacred rituals performed inside to the eternal cycles of the heavens, reinforcing the order's worldview and creating moments of breathtaking theatricality that reinforced their spiritual authority. For an initiate, witnessing the sunbeams strike the exact spot on the day of the winter solstice was a powerful confirmation that they were part of a divinely sanctioned enterprise, their very calendar written in light and shadow upon the stones of their chapel. The genius of this approach was its seamless integration of meaning with structural necessity. These were not mere symbols tacked onto a functional building. The golden ratio, for example, is not only aesthetically pleasing but also creates remarkably stable and efficient structural forms. The octagonal layout of many chapels provided excellent load distribution for heavy stone roofs. The strategic window placements for celestial alignments also serve to illuminate the interior in the most effective way possible at the most important times. The sacred and the practical were two sides of the same coin. A pillar was never just a pillar. It was a structural support, a marker of sacred geometry, and a potential key to understanding the building's deeper cosmological significance. This holistic design philosophy meant that the hidden messages were not vulnerable to erosion or removal. They were intrinsic to the building's very stability and form. The secret knowledge was safe because to destroy the code, one would have to destroy the building itself. Contemporary architects, particularly those designing cultural institutions, memorials, and places of worship, are increasingly looking to these medieval examples for inspiration. In an age often dominated by glass box modernism and purely utilitarian structures, there is a growing desire to recapture that sense of layered meaning, to create buildings that speak to the human spirit on multiple levels. When an architect designs a national memorial today, they are faced with a challenge strikingly similar to that of the knightly builders: how to convey profound, often complex, emotions and ideas without words. Studying cryptographic architecture provides a powerful toolkit: the careful use of proportion to evoke a sense of solemnity or hope, the strategic use of light to create moments of revelation, and the embedding of symbolic geometries that resonate with our subconscious understanding of harmony. All these are lessons learned from chapels and commanderies built 8 centuries ago. A modern memorial might use a descending pathway that narrows according to the golden ratio to create a growing sense of contemplation, or an oculus that aligns with the sun on a significant anniversary, casting a beam of light onto a central plaque. These techniques move visitors beyond mere observation into a state of emotional and intellectual engagement, making the architecture an active participant in telling its story. This pursuit represents a fundamental shift back towards a more integrated, human-centric design philosophy. The knightly orders understood that the most successful architecture serves not just the body, but also the mind and the spirit. Their buildings were designed to inspire awe, to convey secret knowledge, to connect humanity with the cosmos, and to provide a tangible experience of divine order. In our modern rush for efficiency and cost-effectiveness, we have often stripped our buildings of this deeper layer of meaning, creating environments that can feel sterile and soulless. The resurgence of interest in cryptographic and symbolic architecture signals a yearning to build a world that is not only functional but also meaningful, a world where our buildings, like those of the knightly masters, can whisper their secrets to those who know how to listen, and stand as enduring testaments to the enduring human need for beauty, mystery, and connection in the spaces inhabit. But to build structures that could endure for centuries, the knightly orders first had to solve the most fundamental of all architectural problems: where to put them. They couldn't always choose ideal, solid bedrock. Often, the most strategically vital locations for a fortress were on soft, waterlogged riverbanks, shifting coastal sands, or unstable hillsides. This forced them to become pioneers of advanced foundation engineering, developing solutions for unstable ground that would challenge modern builders even with our sophisticated machinery. Their ability to erect colossal stone keeps on what should have been treacherous, sinking soil seems to defy logic. It's a feat that goes far beyond simply digging a deep hole. It was a holistic science of understanding how weight, earth, and water interact deep beneath the surface, creating an invisible underground cradle capable of supporting empires of stone for 1,000 years. Their approach was brilliantly systematic, addressing the problem from multiple angles simultaneously. The first layer of their genius was the concept of the layered foundation. Instead of just placing the castle's massive walls on a single slab of stone at the bottom of a trench, they constructed a complex, multi-tiered base. They would begin by excavating down to the most stable sub-layer they could find, which might still be less than ideal. Then, they would build up a foundation in carefully engineered strata. A bottom layer of large, loosely packed rubble stones would act as a drain, allowing groundwater to flow without building up pressure. On top of this, they would lay a compacted layer of gravel and sand, providing a stable, uniform bed. Finally, they would set the first course of massive, finely dressed foundation stones. This layered system functioned like a shock absorber, distributing the immense point loads of the walls evenly across a wider area of soil and preventing differential settlement, the nightmare scenario where one corner of a building sinks faster than another, causing catastrophic cracking and collapse. Perhaps even more ingenious was their use of underground buttressing. We're familiar with flying buttresses on the outside of cathedrals, but the knightly engineers built their most critical supports where no one could see them. They understood that the pressure from a massive wall didn't just go straight down, it pushed outward as well. To counter this, they extended foundation walls deep into the ground at angles, creating a hidden network of stone ribs that locked the entire foundation together into a single, coherent unit. Think of it as creating a buried stone iceberg. The castle you see above ground is only a fraction of the structure. Below the surface, a vast, interlocked web of stone spreads the building's weight and resists the lateral forces of shifting soil. In marshy areas, they would even drive long, sharpened timber piles deep through the soft upper soil until they hit a firm stratum, then build their stone foundations on top of this reinforced wooden grid. This composite of wood and stone exploited the tensile strength of timber and the compressive strength of rock in a way that modern engineers recognize as an early form of reinforced concrete. The third, and arguably most critical, element was their mastery of subterranean drainage. The knights knew that water was the primary enemy of stability. Saturating the soil beneath a foundation weakens it dramatically, and freezing and thawing can heave stones out of position. Their solution was to integrate drainage into the very heart of their foundations. They didn't just dig ditches, they built sophisticated underground channels, often lined with stone or clay pipes, that actively diverted groundwater away from the building's core. These weren't simple holes in the ground, but carefully sloped conduits that used gravity to create a constant, passive flow, dewatering the soil beneath the fortress and ensuring it remained consistently dry and stable. In some of their coastal castles, these systems were so effective that they kept foundations dry in soil that was perpetually saturated just a few feet away. This proactive management of hydrostatic pressure is a principle that is absolutely fundamental to modern geotechnical engineering, yet these medieval builders implemented it with nothing but empirical observation and brilliant intuition. The proof of their success is standing all across Europe and the Middle East, often in the most geologically improbable places. There are Templar commanderies on the shifting sands of the Mediterranean coast and Teutonic fortresses in the waterlogged plains of Poland that have not settled more than a few inches in 800 years. Modern laser-level surveys of these structures reveal a near-perfect levelness that would be the envy of any contemporary construction project. We build with computer models and soil samples, yet our structures often require underpinning and repair within decades. Theirs, built on what we would classify as problematic ground, have endured centuries of floods, minor earthquakes, and the relentless pull of gravity without complaint. This longevity is a silent, powerful testament to an engineering insight that we are still, in many ways, working to formally decode with our advanced science. This is precisely why modern geotechnical engineers are so fascinated by these medieval sites. They aren't just historical landmarks, they are live case studies in long-term foundation performance. In earthquake zones like California and Japan, engineers study how these layered foundations and hidden buttressing systems allowed castles to flex and dissipate seismic energy rather than shatter. The principles of soil dewatering and load distribution pioneered by the Knights are directly applied in the construction of skyscrapers on reclaimed land in cities like Tokyo and San Francisco, where the ground is inherently unstable. The challenge of building massive, heavy structures on soft, compressible soil is exactly the same today as it was then, only our tools have changed. The knightly orders demonstrated that stability isn't just about brute strength, but about intelligent collaboration with the hidden landscape below. They taught us that to build something truly lasting, you must first understand the earth it stands upon, a lesson that continues to resonate on every challenging construction site across the globe today. Beneath the imposing stone walls and towering keeps of a Templar fortress lay another, hidden fortress, a labyrinthine world of shadow and secrecy. While concentric castles presented an insurmountable physical barrier, the Templars engineered an equally brilliant psychological defense with their hidden escape tunnel networks. These were not mere holes in the ground dug in desperation. They were meticulously planned subterranean highways, engineered for stealth, survival, and sowing paralyzing doubt in the minds of their enemies. In the grim calculus of a siege where every resource and every hour counted, these tunnels provided the ultimate insurance policy, ensuring that the Order's most valuable asset, its trained knights and commanders, could live to fight another day, even if the fortress itself fell. The sophistication of these underground systems was remarkable. A typical network was a masterclass in covert engineering, beginning with multiple, cunningly disguised entry points. A secret door might be concealed behind a rotating section of stone in the chapel, hidden beneath a flagstone in the commander's quarters, or accessed through a dry well in the inner courtyard. These entrances were designed to be undetectable during even the most thorough enemy search. Once inside, the tunnels themselves were feats of civil engineering. They were shored up with timber or stone arches to prevent collapse, and most critically, they incorporated concealed ventilation shafts. These narrow channels, often disguised as natural fissures in the rock or hidden among the roots of trees on the surface, provided a constant supply of fresh air, allowing large groups of people to move through them for extended periods without suffocation. The tunnels didn't just lead randomly into the woods. They emerged at strategically chosen locations far beyond the typical siege lines, perhaps in a dense forest a mile away, a secluded cave system, or on the banks of a hidden river where a boat might be waiting. This ensured that evacuees could truly escape the encirclement, not just pop up in the middle of the enemy camp, but the true genius of these tunnels was their dual purpose. Yes, they were a physical escape route, but they were also a powerful weapon of psychological warfare. The Templars understood that the fear of the unknown could be more debilitating than a known threat. They would deliberately leak rumors or allow hints of the tunnel's existence to reach the besieging army. An attacking commander would then be forced to grapple with a terrifying uncertainty. Were his efforts futile? Could the very knights he had trapped simply vanish overnight? Would they use these tunnels not to escape, but to launch a surprise attack from behind his own lines? This knowledge, or even the suspicion of it, forced a besieger to divert massive resources. He had to station large contingents of his best troops in a wide, exhausting perimeter around the castle, watching for secret exits instead of concentrating all his forces on the main assault. It bred paranoia and distrust within the enemy ranks, as every nighttime sound or rustle in the bushes could be interpreted as a Templar sortie. The tunnels, even when unused, actively weakened the enemy's resolve and fragmented their strategy, turning their own imagination against them. This medieval understanding of how to manipulate an adversary's perception is precisely what makes these designs so relevant to modern security architecture. Today's experts don't study Templar tunnels to build literal secret passages, but to understand the principles of concealed egress and psychological advantage. When architects design high-risk facilities like embassies, data centers, or government command bunkers, they face a similar challenge: how to ensure safe evacuation during a crisis without revealing the escape routes to potential attackers. The modern solution is a direct descendant of the Templar model. Emergency exits are deliberately obscured, blended into the building's facade, or accessible only through a series of secure interior chambers. The goal is to create what security professionals call ambiguity of access, making it impossible for an outsider to know all the ways in or out. This uncertainty forces a potential attacker to spread their resources thin, just like the medieval besieger, unsure of where to focus their assault. Furthermore, the psychological dimension is now a formal part of security strategy. The very design of a modern secure facility is intended to project an aura of impenetrability and to create doubt in the mind of anyone considering an attack. The visible security measures the checkpoints, the cameras, the armed guards are only one layer. The hidden elements, the unseen protocols, and the rumored capabilities act as a powerful deterrent. A potential terrorist cell, for example, might be dissuaded from even attempting an attack on a building if they believe there are secret evacuation protocols that would save key personnel, or hidden counter-assault tunnels that could allow defenders to appear behind them. The Templars intuitively grasp that a defense is strongest when it operates on both the physical and the psychological plane, and this multidimensional approach is now a cornerstone of protecting everything from corporate headquarters to entire national borders. Their stone corridors, dug by candlelight centuries ago, established a blueprint for security that understands the human mind is the ultimate battlefield, and that the most powerful defenses are those that conquer fear and uncertainty long before a single shot is ever fired. The medieval master builders of the knightly orders understood a fundamental truth that still guides the most advanced engineering today. A structure's true strength is measured not when it is pristine, but when it is under attack and partially destroyed. They engineered their fortresses not as single, monolithic entities, but as interconnected systems with built-in backup plans, creating what we now call structural redundancy. This was the art of ensuring that if one critical component failed, the building wouldn't suffer a catastrophic collapse. It could remain standing, remain defensible, and give its inhabitants precious time to adapt, repair, or even mount a counterattack. This forward-thinking approach transformed their stone fortifications into resilient, almost living organisms capable of absorbing tremendous punishment and continuing to function. This redundancy was woven into the very fabric of their designs through several ingenious methods. One of the most critical was the creation of secondary load paths. In a typical building, the weight of the roof and upper floors is channeled down through specific primary supports, a main pillar, a key arch, a central wall. The knights, however, designed their great halls and keeps so that the structural loads were shared across multiple elements. A vaulted ceiling, for instance, wasn't supported by just 4 corner pillars. Its weight was distributed along the entire length of the side walls, which themselves were buttressed by a series of smaller internal partitions and external supports. If a battering ram or a mining tunnel managed to collapse one of those primary pillars, the load wouldn't simply fall straight down. It would automatically shift and transfer to these secondary paths the neighboring pillars, the reinforced walls, the network of arches, all of which were designed to pick up the extra burden temporarily. The ceiling might sag alarmingly, stones might crack and dust might fill the air, but the room would not immediately pancake into rubble. This gave defenders the crucial opportunity to shore up the damage with timber braces or retreat to a still secure section of the fortress, turning a potential disaster into a manageable structural injury. Beyond shared loads, they implemented brilliant fail-safe mechanisms directly into their masonry. A key example can be found in the design of their monumental gatehouses, the most vulnerable point of any castle. The portcullis, the heavy iron or wooden grate that slammed down to seal the gate, was never a single, standalone defense. It was part of a layered sequence. But its structural integration was what made it truly clever. The slot in the stonework that guided the portcullis was often designed with a slight backward angle. If the stonework around the top of the gate was damaged by a siege engine, causing the arch above to deform, this deformation would often jam the portcullis further into its guide slots, effectively welding it in place through the very force of the attack. Instead of the breach creating an open pathway, it actively sealed the most critical choke point. Similarly, drawbridges were counterweighted in such a way that if the lifting chains were severed, the bridge would automatically swing up into the closed position, not crash down. These were not passive structures, they were interactive systems that responded to damage in a way that enhanced rather than diminished their defensive posture. The most holistic expression of this philosophy was the use of distributed structural systems. Instead of relying on a few massive, indispensable walls, the knights employed a cellular design for their living quarters and inner keeps. Think of it as a honeycomb made of stone. The building was divided into many smaller, interlocking spaces by a network of cross walls. Each of these walls provided mutual support to its neighbors. If an external wall was breached, the internal cross walls would continue to carry the vertical loads from above, preventing a progressive collapse from racing through the entire structure. This distributed intelligence meant there was no single point of failure. An attacker couldn't simply knock out one kingpin and watch the entire fortress fall. They had to dismantle it piece by piece, a task that required exponentially more time, effort, and exposure to defensive fire. This approach ensured that even a castle that was technically breached could remain a deadly, complex maze of defensible positions where every corridor and every room could become a new stronghold. The profound relevance of these 800-year-old principles is most vividly seen in the work of modern earthquake engineers. When a major seismic event strikes, the primary cause of death isn't the shaking itself, but the collapse of buildings. The nightly problem of a wall being suddenly removed by a battering ram is eerily similar to the modern problem of a key support column being shattered by an earthquake. In response, contemporary engineers have formalized the medieval concept of redundancy into a principle called progressive collapse prevention. Building codes in seismic zones now mandate that structures be designed with alternative load paths. If a computer model shows that the failure of one critical column would cause a chain reaction collapse, the architect must redesign the building to include redundant beams, transfer girders, or moment-resisting frames that can catch the load, just like the secondary paths in a medieval keep. The goal is identical: localize the failure, allow a portion of the building to be damaged, even destroyed, but prevent that failure from propagating and bringing the entire structure down on the heads of the occupants. This gives people life-saving minutes to escape, transforming a potential catastrophe into a survivable event. What is truly humbling for modern engineers is the realization that the Knights achieved this sophisticated understanding without any of our tools. We use finite element analysis software to simulate stresses and strains across millions of points in a virtual building. We conduct shake table tests with scaled models to observe how complex structures behave under dynamic loads. The master builders of the Teutonic Knights and the Templars had none of this. Their knowledge was built on a foundation of painful, real-world experience, passed down through generations of masons and carpenters. They learned through collapse. They observed which arches held and which fell, which wall configurations survived sapping and which crumbled. They developed an intuitive, almost visceral grasp of structural behavior that allowed them to anticipate failure points and preemptively reinforce them. Their buildings were their computer models, and the sieges were their ultimate stress tests. The fact that their empirical solutions so closely align with our computer-generated conclusions is a powerful testament to the universality of physics and the sheer brilliance of their observational science. Their legacy is literally set in stone, reminding us that resilience is not a modern invention, but a timeless principle of intelligent design. While the knights engineered their fortresses to withstand immense physical force, they also mastered a more subtle weapon, one that targeted an attacker's most vital tool, their vision. Beyond the formidable walls and deadly arrow loops, they employed sophisticated optical defense enhancements, turning sunlight itself into a tactical ally. Imagine an approaching army, shields raised against a hail of arrows, but now confronted by an even more disorienting assault. At key points along the battlements, highly polished metal shields or carefully positioned concave mirrors would catch the full glare of the morning or afternoon sun, focusing it into blinding beams of light that were directed straight into the eyes of the advancing soldiers. This wasn't just an occasional nuisance, it was a calculated system of glare warfare. The effect would be instantaneous and devastating. A knight straining to aim his crossbow or a sapper trying to position his battering ram would suddenly be struck by an unbearable, stabbing light, causing temporary flash blindness, disorientation, and a complete loss of night vision for critical moments. In the chaotic frenzy of an assault where a single misstep could mean death, this visual disruption could break a formation's cohesion and turn a coordinated attack into a confused and vulnerable mob. This manipulation of light extended far beyond directed beams. The entire castle was designed as a stage for controlling visibility and shadow. The strategic placement and shaping of arrow loops and observation slits are perfect examples of this optical genius. From the outside, these narrow openings appeared as mere dark slashes in the stone, offering attackers almost no target to shoot at. But from the inside, they were carefully carved into a splayed form, widening dramatically towards the interior. This ingenious design, often called a fishtail embrasure, created a massive field of view for the defender cowering safely within the thick wall. A single archer could survey a huge swath of the battlefield without moving, tracking approaching enemies while remaining almost completely concealed. The geometry of these slits also managed light and shadow perfectly. The exterior's narrow opening minimized the amount of sunlight entering the defensive position, preventing the archer inside from being backlit and becoming a visible silhouette, a fatal giveaway. Meanwhile, the wide interior aperture allowed what little light did enter to illuminate the defender's space, making it easier to load weapons and see clearly. This control of the visual environment meant that defenders operated with a profound information advantage, seeing without being seen, while their enemies struggled in a disorienting world of blinding glare and impenetrable shadows. The psychological impact of this optical warfare cannot be overstated. It weaponized the environment itself, creating a profound sense of unease and powerlessness among attackers. A fortress that could seemingly command the sun to blind its enemies appeared not just strong, but mystically powerful. The constant, unpredictable flashes of light, the inability to see where arrows were coming from, and the eerie feeling of being watched by invisible defenders from those dark slits in the wall all worked to erode morale. This was an early, brilliant application of environmental psychology. The knights understood that a soldier's perception of the battlefield, what he could see, what he feared, and how in control he felt, was just as important as his physical strength or weaponry. By deliberately designing a space that confused the senses and amplified feelings of vulnerability, they could win a battle before the first ladder even touched the wall. The fortress became not just a physical barrier, but a psychological maze that preyed on the most fundamental human fears of the unknown and the unseen. In the modern world, the legacy of these optical tactics is clearly visible in the security measures protecting everything from military bases to high-security prisons. Contemporary perimeter defense systems have fully embraced the knightly principle of controlling an adversary's vision. Walk the boundary of a sensitive installation at night, and you will likely encounter powerful, strategically placed floodlights. But these are not meant to simply illuminate the area. They are positioned to create what security experts call dazzle and contrast. The lights are aimed to shine directly outwards into the approach paths of any potential intruder, deliberately creating intense glare that makes it difficult to see the guards, cameras, or defensive positions inside the perimeter. Meanwhile, the defenders within the base operate from zones of controlled shadow, their own night vision preserved by the very lights that blind their opponents. This modern dazzle fence is a direct high-tech descendant of the polished shields on the battlements of cracked chevaliers. The underlying principle is identical: seize control of the visual field to disorient and disadvantage the attacker while preserving the clarity and composure of the defender. This philosophy extends even further into the realm of active military camouflage and vehicle design. Modern armies use specially developed paints and materials that don't just blend with the background, but also manipulate light to break up the recognizable silhouette of a tank or aircraft. These patterns, often angular and contrasting, are designed to confuse an observer's depth perception and make it difficult to determine the object's exact distance, speed, and shape. It is a more sophisticated evolution of the knightly use of shadow and light patterns across a castle's stone facade to make its true dimensions and features harder to discern from a distance. Even the design of modern armored vehicle periscopes and vision blocks incorporates the same anti-glare principles as the medieval arrow loop, using layers of filtered glass and specific angles to protect the occupant's vision from laser dazzle weapons or the flash of explosions. The fundamental understanding remains unchanged. In any conflict, the side that best controls the visual environment holds a decisive edge. The knights, with their mirrors and meticulously carved stone, were the early pioneers of this form of perceptual warfare, proving that the most effective defense is often one that conquers the enemy's ability to perceive the battlefield clearly, turning their greatest asset, their own eyes, into a source of confusion and weakness. This philosophy of integrated design reached its absolute pinnacle in the knightly order's mastery of multi-purpose structural elements. In their world, every stone, every beam, every architectural feature was expected to pull its weight in multiple, often surprising ways. A single, massive pillar in a Templar chapter house was never just a pillar. Its primary, obvious function was to hold up a heavy stone vault, channeling immense gravitational forces safely into the ground. But if you were to examine that same pillar more closely, you might discover that its core was hollow, containing a narrow, spiraling staircase that led to a hidden chamber in the roof space, used for secure meetings or as a last resort defensive position. On its exterior surface, carefully carved channels, invisible to the casual glance, would direct condensation and rainwater down into a concealed cistern, contributing to the fortress's water supply. And the very proportions of the pillar, its diameter and height, might be calculated according to the sacred golden ratio, encoding a message of divine harmony into the heart of the structural frame. This single element was at once a support, a secret passage, a utility, and a theological statement. Nothing was wasted. Every component was a multi-tool crafted in stone. This approach required a radically different kind of design thinking, one that considered a building as a single, complex, interconnected organism rather than a collection of separate systems. The architects had to hold multiple, overlapping intentions in their minds simultaneously. When designing a fortress wall, they weren't just asking, "Is it thick enough to stop a projectile?" They were also asking, "Can we route ventilation for the latrines through its core? Can we design the battlements to cast specific shadows that disorient attackers at dusk? Can the pattern of the stonework itself signal membership ranks to initiates?" This holistic vision meant that the structural, the practical, and the symbolic were fused at the moment of conception. A vaulted ceiling wasn't designed first for strength and then decorated with symbols later. The symbolic geometry was the structural form, each supporting the other in a beautiful, self-reinforcing loop. This eliminated the modern concept of cladding or superficial decoration. The beauty and the meaning were inherent, emerging directly from the building's physical necessities and structural logic. The efficiency gains from this methodology were staggering. By having one stone do the job of 3 or 4, the knightly builders achieved an incredible economy of material. They constructed more with less, reducing the quarrying, transportation, and labor required for a project. This was not just a matter of cost saving, it was a form of medieval sustainability. In an era without industrial production, the energy embodied in materials was immense, and minimizing waste was a critical imperative. This multifunctionality also created structures of remarkable resilience and adaptability. If a primary function of a space became obsolete, the building could often be repurposed with ease because its core elements already served multiple roles. A chapel could become a fortified granary because its pillars were already load-bearing and its walls were already thick enough for defense. This inherent flexibility stands in stark contrast to many modern single-use buildings, which can become useless shells when their original purpose fades. Today, this medieval principle of multi-purpose design is experiencing a dramatic renaissance under the banner of sustainable architecture. Modern architects facing a climate crisis are fundamentally rethinking the profligate waste of the 20th century, where buildings were often designed with separate, additive systems for structure, cladding, mechanical services, and interior finishes. The new paradigm, heavily influenced by studying these ancient structures, is often called monomaterial or design for disassembly. The goal is to emulate the knightly builders by having primary structural elements perform multiple environmental tasks. A contemporary example might be a building's concrete floor slab, which is now often designed to act as a thermal mass, absorbing heat during the day and releasing it at night, thereby regulating the interior temperature passively. At the same time, this same slab might contain capillary tubes for radiant heating and cooling, transforming it from a mere floor into the building's primary climate control system. The structure itself becomes the machine for living, eliminating the need for separate, energy-intensive air handling units and ductwork. This holistic integration is the holy grail of modern sustainable design, and the knightly orders provided a masterclass in its execution. Their work demonstrates that the most elegant and enduring solutions arise when we stop thinking in compartments. The modern world has become dominated by specialization, where a structural engineer, a mechanical engineer, an acoustician, and an interior designer might all work in separate silos, leading to buildings that are often inefficient, full of conflicting systems, and environmentally costly. The medieval master builder, by contrast, was a generalist genius who held all these disciplines in one mind. He understood that a building is a single, complex system where a change in one area ripples through all the others. By designing for this interconnectedness from the very beginning, he created structures of profound efficiency, resilience, and layered meaning. Their legacy challenges us to move beyond our fragmented design processes and rediscover the power of unity, proving that the most advanced building is not the one with the most technology bolted on, but the one where every element, from the largest foundation stone to the smallest carving, is working in harmonious, multi-layered concert. Now we come to a feat of engineering that seems to defy one of the most basic laws of nature, the fact that materials expand and contract with heat and cold. For any large stone structure, the relentless cycle of daily and seasonal temperature changes is a silent, insidious enemy. A castle wall baking in the summer sun can be dozens of degrees hotter than its shaded foundation, causing the stone to expand minutely but powerfully. Then, during a freezing winter night, the same wall contracts. Over decades and centuries, this constant push and pull can cause even the mightiest masonry to crack, spall, and eventually fail. The knightly orders confronted this fundamental problem not by fighting it, but by collaborating with it through the brilliant integration of metal and stone. They pioneered advanced metallurgical techniques, weaving iron and lead into the very fabric of their buildings to create composite structures that were not just strong, but dynamically flexible, able to dance with the rhythms of the seasons without missing a step. The most common and crucial application of this was the use of iron cramps and tie rods. In great halls and chapter houses, where wide, open spaces were essential, the knights needed to support heavy stone vaults and roofs. Stone is incredibly strong under compression. It can bear immense weight pushing down on it, but it is notoriously weak under tension, the pulling or stretching force that tries to bend a horizontal stone beam or pull the walls of a wide room inward. To solve this, the builders would embed massive iron tie rods high up in the structure, running horizontally from one wall to another, often hidden within the masonry or just below the roof line. These rods, sometimes inches thick, acted like permanent, unbreakable belts, cinching the walls together and counteracting the outward thrust from the heavy roof. They provided the tensile strength that stone alone could not, allowing for more daring and expansive interior spaces. But the true genius wasn't just in adding the iron. It was in how they managed the inevitable interaction between the two materials. This is where their deep, intuitive understanding of material science becomes truly apparent. The knights knew that iron and stone expand and contract at different rates when heated. If they simply locked an iron rod rigidly into a stone wall, the metal would expand slightly more than the stone in the summer heat, creating immense pressure that could crack the surrounding masonry. In the winter, as the metal contracted more sharply, it could loosen in its socket, compromising the entire system. Their solution was both simple and sophisticated. They did not fix the metal ends solidly. Instead, they often seated the ends of these great iron rods in specially designed pockets or lead sockets. Lead is a soft, malleable metal that acts as a perfect mediator. When the iron expanded, the lead would compress and flow, absorbing the stress without transmitting destructive force to the brittle stone. When the iron contracted, the lead would expand to fill the gap, maintaining a snug, secure fit. In other cases, the ends of the rods were forged with eyelets and pinned, not mortared, allowing for a tiny amount of pivotal movement. This careful engineering acknowledged the independent life of each material, giving them the freedom to move in harmony rather than locking them into a destructive struggle. Beyond these large structural ties, metal was integrated in thousands of smaller, yet equally vital ways. They used durable iron pins to lock adjacent stone blocks together, preventing them from sliding past one another. Windows and door frames, the most vulnerable points in any wall, were often reinforced with iron casings. They even employed lead as a waterproofing and leveling agent, pouring it into joints or using it as a bedding material for delicate carved work. In every instance, the choice of metal, its shape, and its method of attachment were carefully considered based on its specific role and location within the structure. This wasn't a one-size-fits-all approach. It was a bespoke, material-specific strategy that treated metal as an active, living component of the architectural whole. The proof of their success is written in the longevity of these buildings. Many medieval cathedrals and castles that have survived for 8 centuries show remarkably little structural distortion from thermal stress, especially when compared to modern concrete structures from just a century ago that often exhibit significant cracking. Modern restoration architects tasked with preserving these ancient monuments have become forensic experts in these medieval metalworking techniques. When they disassemble a section of wall for repair, they often find these original iron clamps, still sound and functional after hundreds of years of temperature cycles, nestled in their protective beds of lead. Studying these assemblies has led to a revolution in conservation philosophy. Instead of replacing old iron with modern steel, which behaves differently, conservators now often seek to preserve and stabilize the original components, understanding that the historical system was perfectly engineered for its purpose. They have also adapted the principle, using modern, non-corrosive alloys and flexible polymers to create new, sympathetic reinforcement that respects the original building's need to move and breathe. This medieval solution speaks directly to a persistent challenge in modern construction. Today, we frequently combine materials like concrete, steel, glass, and aluminum in the same building, each with vastly different coefficients of thermal expansion. The squeaks and groans you sometimes hear in a modern building on a hot day are the sounds of these materials in conflict, straining against each other. We manage this with complex expansion joints and slip planes, but it remains a primary cause of long-term maintenance issues, water infiltration, and facade failures. The Knights' work demonstrates that durability isn't just about choosing strong materials, but about understanding how they will live together over time. Their buildings were designed not for a moment in time, but for all time, with a foresight that considered the endless cycle of day and night, summer and winter. In an age increasingly concerned with building resilience and reducing waste, their mastery of material compatibility offers a powerful lesson in creating structures that are not only strong upon completion, but are engineered to remain that way for generations to come, gracefully enduring the relentless passage of the seasons. Beyond the physical intimidation of towering walls and the lethal efficiency of their defensive systems, the knightly orders perfected a more insidious form of power, one that targeted the mind itself. They engineered psychological warfare architecture, transforming stone and space into instruments of intimidation and control. This was architecture as a form of theater, carefully staged to produce specific emotional responses, ensuring that from the moment a visitor or an enemy laid eyes on a commandery, they were plunged into a carefully crafted psychological landscape designed to amplify their fears and diminish their sense of agency. The fortress was not just a shell of defense, it was an active participant in the battle for morale, a silent, looming opponent that worked to break wills long before a single sword was drawn. Consider the experience of approaching a Teutonic Knights fortress as a diplomatic envoy from a rival power. Your journey would begin with a long, exposed approach, forcing you to cross open ground under the watchful eyes of sentries high above. As you drew nearer, the sheer scale of the structure would become overwhelming, its walls seeming to lean out over you, a deliberate effect created by battered bases that sloped inward as they rose. You would then arrive at the gatehouse, but not at a welcoming, human-scale door. Instead, you faced a monstrous, recessed entrance, a deep, shadowy tunnel bored through perhaps 50 feet of solid stone. The actual doorway at the far end was small and low, forcing you to stoop to enter. This sequence was a masterclass in scale manipulation. The overwhelming bulk of the gatehouse made you feel insignificantly small, while the act of bowing your head to enter was a physical enactment of submission, a psychological victory for the defenders before you had even spoken a word. Once inside this tunnel, you might find yourself in a narrow, twisting passage, dimly lit and punctuated by multiple iron portcullises suspended ominously overhead, their sharpened points at eye level. The message was unmistakable. You were a rat in a trap, your fate entirely in the hands of the unseen powers controlling this labyrinth. Inside, the psychological manipulation continued through deliberate auditory and spatial disorientation. The acoustic properties we discussed earlier weren't only for the benefit of the defenders' communication, they were also weaponized against visitors. A grand hall might be engineered to amplify the sound of the commander's voice from the high table, making his pronouncements boom with divine authority, while simultaneously muffling the whispers and shuffling feet of his guests, making them feel isolated and unheard. Corridors might suddenly narrow or change direction for no apparent structural reason, creating a sense of unease and confusion. A staircase might rise in an unpredictable spiral, with uneven treads designed to trip up an unfamiliar foot. For the resident knights who had trained and lived in this environment for years, these paths were second nature. They moved with an efficient, confident grace that further highlighted the visitor's vulnerability and clumsiness. This created a powerful insider versus outsider dynamic, where the knights were the masters of a complex, almost magical domain, and everyone else was merely a disoriented guest, constantly off balance and psychologically subjugated. The modern world has eagerly adopted and refined these principles of psychological architecture, though often for vastly different purposes. Architects designing maximum security prisons study the knightly blueprint to create environments that manage inmate behavior and minimize violence. The approach to a modern supermax facility often recreates that same sense of overwhelming scale and controlled access, establishing institutional authority from the very first moment. The interior layouts are deliberately disorienting, with color-coded pathways for guards and confusing, monotonous corridors for inmates, preventing them from forming a coherent mental map of their surroundings, and thus reducing their ability to plan disturbances or escapes. The goal, much like in a medieval fortress, is to create a population that feels controlled and observed, reducing the likelihood of conflict through environmental design rather than sheer brute force. Yet this understanding of psychological space is not solely the domain of security. Museum designers now use these same principles to guide visitor emotion and focus. The journey through a Holocaust memorial, for instance, might intentionally incorporate narrow, descending pathways and oppressive, low ceilings to evoke feelings of claustrophobia and despair, preparing the visitor emotionally for the exhibits within. Conversely, a museum celebrating human flight might use a vast, soaring atrium to instantly inspire feelings of awe and possibility. Memorials like the Vietnam Veterans Memorial in Washington, D.C. use the powerful combination of scale and descent, the way the black granite wall grows taller as you walk down into the earth, to create a profound, personal, and emotionally devastating experience. The architects are not just building a structure, they are choreographing a psychological journey using the same tools of scale, progression, and spatial sequencing that a Teutonic Knight would have recognized instantly. This sophisticated application means that the knightly orders were, in fact, the unacknowledged pioneers of environmental psychology, the formal study of how our surroundings influence our thoughts, feelings, and behaviors. They intuitively grasped concepts that would only be named centuries later, such as prospect refuge theory, the idea that humans are most comfortable in spaces where they can see without being seen. Their fortresses offered countless refuge spots for defenders concealed behind arrow slits, while denying any prospect or clear view to attackers in the killing zones below. Their work demonstrates that architecture is never neutral. Every doorway, every corridor width, every ceiling height sends a silent message, either of welcome and empowerment or of intimidation and control. The knights simply elevated this silent language to a high art, crafting stone sentences that spoke directly to the subconscious, mastering the terrain of the human mind with the same ruthless efficiency they applied to the conquest of land. While their fortresses projected an image of stark military power, the true, hidden strength of the knightly orders lay in their mastery of a quieter, more profound art, the creation of self-sustaining ecosystems. A Teutonic commandery or a Templar preceptory wasn't just a barracks, it was a meticulously engineered life support system, a closed-loop community designed to thrive in isolation for years, completely cut off from the outside world. This went far beyond simple stockpiling. It was a holistic philosophy of resource independence, where every input was maximized, every waste product was repurposed, and the very cycles of nature were harnessed within the fortress walls. A besieging army might see a silent, impregnable stone shell, but inside, a vibrant, self-sufficient world was humming with activity, its resilience guaranteed not by the thickness of its walls alone, but by the brilliance of its integrated resource management. Consider the challenge of food. A fortress needed to feed hundreds of knights, sergeants, craftsmen, and their families indefinitely. Stockpiling grain in sacks would only last so long before rot, pests, or mold would destroy it. The knightly solution was architectural. They constructed specialized food preservation chambers that were feats of passive environmental engineering. These were often semi-subterranean vaults, built into the north-facing side of a keep or carved directly into the bedrock beneath a courtyard. Their thick stone walls provided immense thermal mass, maintaining a cool, consistent temperature that changed little between summer and winter. But the real genius was in the ventilation. Carefully designed air channels, often exploiting the stack effect, would draw cool air from shaded underground passages or well shafts, creating a constant, gentle breeze that circulated through the stored grains and salted meats, preventing moisture buildup and spoilage. Some chambers even incorporated layers of certain types of clay or salt blocks into their walls, which would actively absorb ambient humidity from the air. In these naturally refrigerated, dry, and dark spaces, food supplies could remain viable not for months, but for many years, turning a siege from a race against starvation into a manageable long-term stalemate. But sustainability isn't just about preservation, it's about production and renewal. The Knights were pioneers in capturing renewable energy long before the term existed. Within their compounds, you would often find water wheels, not just for grinding grain, but as the primary power source for a variety of workshops. A single wheel on a diverted stream could operate trip hammers for a blacksmith's forge, power bellows, run saws in a carpentry shop, and even operate laundry paddles. This mechanical energy was the medieval equivalent of electricity, and they distributed it throughout their industrial quarters. Furthermore, they mastered wind-catching technology. In their Middle Eastern strongholds, they built clever wind towers or malkafs on their roofs. These tall, chimney-like structures would capture the prevailing breezes high above the ground and funnel them down into the living quarters and infirmaries, providing natural air conditioning. The incoming air was often channeled over underground cisterns of cool water, chilling it further before it entered the rooms. This provided a level of comfort and sanitation that was unimaginable in most contemporary dwellings, all without consuming a single log of firewood. Perhaps the most advanced aspect of their system was its approach to waste, which was not seen as an endpoint, but as the beginning of a new cycle. Knightly compounds operated with a cradle-to-cradle mentality that would be the envy of any modern eco-village. Human and animal waste was not simply discarded. It was systematically collected in sealed, stone-lined cesspits where it would compost safely. This resulting night soil was then a vital resource, carefully applied to the extensive gardens and orchards within the fortress walls or in protected plots immediately outside. These gardens were not just for show. They were intensive agricultural operations growing vegetables, herbs, and fruit trees, fertilized by the very community they fed. Even grey water from kitchens and bathhouses was channeled through settling tanks and then used for irrigation. Ash from the hearths and forges, rich in potassium, was saved and used to amend the soil. This created a perfect closed nutrient loop. Food was consumed, its waste byproducts were processed, and those processed materials returned to the soil to grow more food. The fortress, therefore, was not a consumer of resources, but a generator of them, a living organism that sustained itself through its own carefully managed metabolic processes. The modern relevance of this medieval closed-loop thinking is nothing short of revolutionary. As contemporary architects and urban planners grapple with the immense challenges of climate change and resource scarcity, they are increasingly looking to these knightly models for inspiration. The principles of passive food storage are being reimagined in the design of modern buildings with root cellars and earth-sheltered pantries for off-grid living. The concept of capturing on-site energy from water and wind is the direct philosophical ancestor of today's solar panels and micro-hydro turbines, but the most significant lesson is in the holistic, systemic view of waste. The modern circular economy movement, which seeks to eliminate waste by designing products and systems where materials are continuously reused, is a direct echo of the Teutonic Knights' nutrient cycle. Today, we see this in advanced ecological wastewater treatment systems that use constructed wetlands to purify water naturally, or in buildings that compost organic waste on site to create fertilizer for green roofs and vertical gardens. This comprehensive approach offers a powerful blueprint for designing the resilient communities of the future, whether they are remote research stations in Antarctica, planned eco-cities in arid regions, or even long-duration space habitats for missions to Mars. The core challenge is identical: how to create a thriving, healthy human habitat with minimal or even zero external inputs. The knightly orders proved that it is possible to engineer not just a defensive structure, but a life-sustaining ecosystem. Their compounds were microcosms of a sustainable world, demonstrating that true resilience comes from interconnection and regeneration. In an era of fragile global supply chains and environmental uncertainty, Their ancient wisdom teaches us that our greatest security may not lie in building stronger walls to keep the world out, but in designing smarter systems that allow us to live harmoniously and self-sufficiently within our own means, turning our settlements from resource drains into net producers of life and energy. Imagine a fortress that doesn't just exist under the sky, but actively converses with it. For the knightly orders, architecture was a bridge between the earthly and the celestial, and their most sacred and strategic buildings were ingeniously engineered to function as monumental calendars and fixed observatories. This wasn't mystical speculation, it was precise, practical science carved in stone. They designed specific windows, narrow slits, and even the alignment of entire walls to capture the sun's rays at pivotal moments of the year. On the morning of the winter solstice, for instance, a single, brilliant shaft of light would pierce the gloom of a Templar chapel, striking a particular carving on the far wall or illuminating a specific flagstone on the floor. This transient event, lasting only a few minutes, was a moment of breathtaking certainty. It marked the turning of the year, the point after which the days would begin to grow longer, a symbol of hope and renewal that was physically manifested within the sacred space. Similarly, the alignment for the summer solstice or the equinoxes, when day and night are of equal length, served as a built-in reset for their liturgical calendar, ensuring that important feast days were observed with celestial accuracy, connecting their daily prayers and rituals directly to the grand, cosmic clockwork overhead. The methods they used to achieve this precision reveal a sophisticated understanding of geometry and solar paths. One of the most common techniques was the light spot or meridian line method. A small, carefully calibrated hole was drilled in a south-facing wall at a specific height and angle. This opening, known as a gnomon hole, acted like a camera obscura, projecting a tiny, distinct disk of sunlight onto the chapel's interior floor. Throughout the year, this spot of light would travel along a predictable path. On the equinoxes, it would cross a line etched into the stone, marking the moment of perfect balance. On the solstices, it would reach its northernmost or southernmost extreme, a clear, undeniable indicator of the sun's standing point. In some larger commanderies, the architecture itself was the instrument. The main axis of a church might be aligned so that the rising sun on the feast day of the order's patron saint would shine directly down the nave, flooding the altar in a divine, golden light. This transformed the entire building into a solar temple for a few glorious minutes, creating an immersive experience that reinforced their spiritual identity and demonstrated a harmonious relationship between their faith and the fundamental laws of the universe. This celestial awareness was not confined to their places of worship. It was a crucial component of their military planning. A fortress that could accurately track the seasons held significant strategic advantages. Knowing the precise date of the winter solstice allowed a commander to calculate how many weeks of poor weather remained before spring campaigning could begin. It informed decisions about rationing supplies, as the length of daylight directly impacted the ability to conduct repairs, train troops, or patrol the surrounding lands. The ability to independently and accurately mark the passage of time, without relying on error-prone lunar calendars or external information, was a form of operational intelligence. It meant that a besieged garrison, completely cut off from the outside world, could still maintain an accurate internal calendar, helping to predict the duration of their ordeal and plan their defense accordingly. The very stones of their fortress provided them with a reliable, perpetual almanac, turning architecture into a tool for temporal navigation and strategic foresight. Today, architects designing planetariums, museums of science, and educational centers are looking back to these medieval models with renewed interest. The challenge they face is strikingly similar: how to create buildings that don't just house exhibits about the cosmos, but that themselves teach and inspire a connection to it. Modern cultural institutions now often incorporate architectural features that track celestial events, much like the nightly chapels. A contemporary science museum might feature a rooftop aperture that projects a beam of sunlight onto a meridian line in the main atrium, allowing visitors to witness the equinox firsthand. The design of the new Stanford University Solar Observatory, for instance, uses a precisely angled light shaft to illuminate a central plaque only on the summer solstice, creating a modern ritual of cosmic awareness. These designs aim to break down the barrier between the indoors and the outdoors, between human-made environments and the natural world, fostering a sense of wonder and belonging in a vast, ordered universe. This pursuit represents a profound shift in design philosophy, a move away from buildings as sealed, artificial boxes and toward architecture as a mediating element between humanity and nature. In our modern, urbanized world, we have become increasingly disconnected from the fundamental rhythms that governed human life for millennia. We live by the artificial glow of screens and the rigid ticks of digital clocks, often unaware of the moon's phase or the sun's position in the sky. The knightly orders, by contrast, lived and built within this cosmic context. Their seamless blending of practical necessity with astronomical observation demonstrates a holistic worldview that saw no separation between the spiritual, the military, the practical, and the celestial. They understood that to build was to participate in a larger order, and their structures stand as timeless reminders that our most meaningful and enduring architecture is that which helps us find our place, not just on the earth but in the cosmos. Their silent stone sentinels, aligned to the motions of the heavens, challenge us to look up and rediscover the sky, not as a distant void, but as the ultimate measure of our time and the most inspiring blueprint for a connected, meaningful existence. But conquest is only half the story. The true test of an empire is what you build with what you've taken. Across the varied landscapes of the Holy Land, the Baltic, and the Mediterranean, the knightly orders frequently found themselves in possession of formidable structures they had not originally built: Byzantine watchtowers, Islamic fortresses, even ancient Roman ruins. Demolishing these and starting from scratch was often impractical, a slow and resource-draining process they could not afford in hostile territory. Instead, they became the undisputed masters of adaptive reuse engineering, developing a systematic, almost surgical approach to remaking captured architecture for their own unique needs. This wasn't mere renovation, it was a form of architectural alchemy, transforming the defensive logic of one culture into the hardened stronghold of another with breathtaking speed and ingenuity. The process began with a ruthless and pragmatic assessment. A team of knight engineers, often accompanied by experienced masons, would conduct a thorough survey of their newly acquired prize. They weren't just looking for its strengths, they were actively seeking out its hidden weaknesses from a defender's perspective. How could an enemy exploit this low wall? Was that gatehouse vulnerable to mining? Were there blind spots in the field of fire from the existing arrow slits? Their first interventions were often brutally logical and focused on reinforcing the existing skeleton. If a wall was strong but not tall enough, they didn't tear it down. They built upwards, adding several new courses of masonry right on top of the old, carefully keying the new stones into the existing fabric to create a single, unified structure. To counter the threat of siege towers, they might add a massive, protruding talus, a sloping stone skirt, to the base of the walls, causing battering rams to glance off and making it much harder to undermine the foundation. A square Roman tower, vulnerable to the corner-shattering impact of a trebuchet stone, would be encased in a new, rounded mantle of stone, transforming its profile into a more resilient, deflection-friendly shape. Each of these modifications was a direct response to a specific tactical problem, applied with the precision of a military surgeon operating on a living patient. The real genius, however, lay in their ability to fundamentally reconfigure the internal logic of a building. A captured structure was designed around the lifestyle and combat doctrines of its original owners. The knightly orders had to imprint their own identity upon it. A sprawling Islamic palace complex with its series of open courtyards and private reception halls presented a defensive nightmare. The knight's solution was to selectively break and remake the internal circulation. They would wall up grand, decorative archways that created vulnerable open sightlines, forcing movement through a new, controlled network of narrow, defensible corridors. They would insert new internal partitions to create killing zones and choke points where none existed before, turning a palace of pleasure into a fortress of war. In one remarkable example, the Hospitallers at Crac des Chevaliers took an existing structure and didn't just add a second wall. They completely re-engineered the water system, the storage areas, and the troop barracks to support a garrison 10 times the original size, all while the fortress remained operational. This ability to perform open-heart surgery on a building's functional core without killing the patient demonstrates an understanding of structural modification that was centuries ahead of its time. This medieval mindset of creative reinvention is the direct intellectual ancestor of the entire modern field of historic preservation and adaptive reuse. Today's architects and renovation specialists face a remarkably similar challenge: how to give a historic building, a factory, a school, a church a vibrant new life for the 21st century without erasing the patina of its past. The principles the Knights pioneered are now standard practice. When converting a massive, brick-built 19th century warehouse into modern apartments, for instance, engineers must carefully assess the existing structural skeleton, just as the Knights did. They identify load-bearing walls that must be preserved and non-structural partitions that can be removed to create open-plan living spaces. They reinforce old timber floors with steel beams to meet modern safety codes, a direct echo of the Knights adding stone ribs to support a weakened ceiling vault. The central dilemma is identical: how to honor the original fabric while fearlessly making the changes necessary for a completely new function, ensuring the building remains useful, safe, and economically viable for generations to come. Perhaps the most profound lesson from the knightly approach is its inherent sustainability, a value we are only now fully appreciating. In an age obsessed with the carbon footprint of construction, the greenest building is overwhelmingly the one that is already built. The knightly orders understood this in terms of resource efficiency. By reusing an existing structure, they saved the immense embodied energy of quarrying, transporting, and shaping countless new stones. They saved time, which in a military context was the most precious resource of all. Their work stands as a powerful 800-year-old argument against the wasteful cycle of demolition and new construction that characterizes so much of our modern development. They demonstrated that the most elegant and intelligent solution is often not to build anew, but to build upon, to reinterpret, and to reinvent. Their fortresses, layered with the architectural DNA of multiple cultures and centuries, are monuments to this flexible, resilient philosophy. They teach us that our built heritage is not a static museum piece to be preserved under glass, but a dynamic, living resource that can be continually adapted, offering its strength to the future if we have the wisdom, as they did, to see the potential hidden within its ancient walls. Now we move from the overt display of power to the art of strategic invisibility, where the knightly orders demonstrated that sometimes the best way to defend a secret is to hide it in plain sight. Their mastery of camouflage and concealment techniques transformed their fortifications into masters of disguise, structures that could blend seamlessly into a rugged hillside or a dense forest, their true defensive prowess deliberately masked behind a facade of apparent weakness or insignificance. This was not about making a castle disappear entirely, an impossible feat, but about controlling the narrative of its strength, manipulating an enemy's perception to such a degree that they would either underestimate the threat entirely or be unable to accurately assess its most vulnerable points. A fortress that looked like a simple, poorly maintained outpost might, in reality, conceal reinforced walls, hidden artillery positions, and a garrison of elite knights, all waiting for an attacker to take the bait. The methods they employed were remarkably sophisticated, beginning with a deep, intuitive understanding of the local landscape. Before a single stone was laid, the master builders would spend weeks, even months, studying the site. They weren't just looking for the most defensible high ground, they were searching for the most inconspicuous high ground. A commandery might be nestled into the side of a cliff, its stone-colored and textured to match the surrounding rock face so perfectly that from a distance, its walls were virtually indistinguishable from the natural stone. In forested regions like those of Prussia, the Teutonic Knights would often leave a thick screen of ancient trees standing between their fortress and the most likely approach routes. This living curtain did more than just hide the walls. It also forced any approaching army into confined, unpredictable paths, negating their numerical advantage and making it impossible to form a coherent battle line for a direct assault. They even manipulated the terrain itself, creating artificial hills or earthworks that reshaped the land to conceal the lower levels of their fortifications, ensuring that the most formidable defensive features remained hidden until an attacker was dangerously close. Color and material selection played a crucial role in this visual deception. The knights were adept at using locally quarried stone, not just for convenience, but for its perfect chromatic harmony with the environment. A fortress built of the same gray limestone as the mountain it stood upon would visually recede into the background. They went a step further, sometimes using different types of mortar or allowing lichens and mosses to grow on specific surfaces to accelerate this process of visual integration, making a new building look as ancient and unremarkable as the landscape itself. More cleverly, they practiced a form of architectural misdirection. A conspicuously strong-looking gatehouse might in fact be a decoy, the most heavily fortified part of the wall, designed to draw an attack toward a killing zone. Meanwhile, the actual, less imposing entrance would be hidden around a bend or behind a natural feature, its defenses deliberately understated to avoid drawing attention. The goal was always to present a false hierarchy of targets, to make the weak points look strong and the strong points look weak, completely scrambling an enemy commander's tactical calculus. This medieval art of perceptual manipulation is a cornerstone of modern military and security architecture. Today's designers of sensitive facilities, underground command bunkers, intelligence agency headquarters, and weapons storage sites face the same challenge the Knights did: how to protect something without advertising its importance. The solution is often to hide in plain sight, just as the Teutonic Knights did. A modern strategic missile silo, for instance, isn't housed in a gleaming, futuristic tower. It is concealed beneath an innocuous-looking agricultural shed or a nondescript concrete pad in a remote field, its terrifying power completely invisible from the surface. The entrances to top-secret subterranean facilities are frequently designed to look like mundane industrial buildings or even private residences, their bland, utilitarian architecture deliberately chosen to deflect curiosity and blend into a commonplace suburban or rural landscape. The principle is identical to the knightly practice of making a fortress look like a simple manor house. By not looking like a high-value target, the structure avoids becoming one. What makes this approach so enduringly powerful is its deep roots in psychological warfare. The knightly orders understood that defense is not merely a physical contest but a cognitive one. The most effective defense plays out in the mind of the potential attacker long before the first assault begins. By creating ambiguity and doubt, they seize the psychological initiative. An army approaching a castle that was expertly camouflaged would be plagued by uncertainty. How many soldiers were inside? Where were the traps? Was this even the main stronghold or just a forward outpost? This ambiguity could cause hesitation, lead to poor tactical decisions, and sap the morale of troops who felt they were fighting an enemy they could not properly see or understand. The fortress became a psychological entity, a silent adversary that used deception as its primary weapon. This concept of perception management is now a formal doctrine in modern military strategy, encompassing everything from the camouflage patterns on a soldier's uniform to the design of stealth aircraft that are difficult to detect on radar. The Knights demonstrated that the battlefield is, first and foremost, a landscape of the mind, and that by controlling what an enemy believes they see, you can control the battle itself. Their silent stone sentinels, masters of disguise rooted in the medieval world, established a timeless truth that what remains unseen and unknown is often far more powerful and terrifying than any visible threat. The true magic of a knightly fortress wasn't always in its sheer bulk, but in its hidden skeleton, an invisible web of intelligence that guided immense weights along predetermined paths with the precision of a master architect. This was the genius of progressive structural loading, a system where every stone was part of a calculated network, a collaborative effort to channel the relentless force of gravity along the most efficient routes possible. Where a less sophisticated builder might simply stack thicker and thicker walls to support a heavy tower, the knightly engineers acted more like sculptors, carving away the unnecessary and directing the loads through a graceful, internal latticework of arches, ribs, and vaults. This allowed them to achieve the seemingly impossible, constructing walls that were surprisingly thin and elegant, yet capable of supporting staggering weights, and creating vast, open interior spaces like great halls and chapter houses that felt airy and expansive rather than cramped and oppressive. They were essentially creating the medieval equivalent of a modern steel frame, but doing it entirely in stone, using geometry as their engineering software. To understand how this worked, picture a massive stone vault spanning the ceiling of a Templar hall. The weight of that vault is immense, and its natural tendency is to push outward, to splay the walls apart and collapse in on itself. A crude solution is to build enormously thick, buttress-like walls to simply resist this outward thrust through brute force. The knightly approach, however, was far more elegant. They designed the vault not as a single, monolithic slab, but as a network of slender, interlocking stone ribs. These ribs, the Gothic equivalent of steel I-beams, carried the primary load. The weight of the ceiling was concentrated onto these ribs, which then channeled it down to specific, heavily reinforced points on the walls. Between the ribs, the builders could fill in with much thinner, lighter panels of stone, reducing the overall weight dramatically. This was just the beginning of the load's journey. The force collected at the top of the wall was then met by another brilliant innovation, the flying buttress. This external stone arm reached out from a freestanding pier to catch the outward thrust from the vault and channel it down and away from the main wall. The entire structure became a dynamic equilibrium of forces, with weight being collected, transferred, and ultimately dissipated into the ground along a series of carefully choreographed paths. The main wall itself, freed from the burden of resisting the vault's push, could be made taller and pierced with large windows, flooding the interior with light. What is truly staggering is that these medieval builders achieved this without the mathematical tools we take for granted today. They had no calculus, no stress analysis software, no understanding of physics as a formalized science. Their method was one of intuitive geometry and accumulated, hard-won experience. They worked from precise geometric rules and proportions that were passed down through generations of master masons. They knew, for instance, that a pointed arch was not just a religious symbol. It was a more efficient structural form than a rounded Roman arch, as it channeled loads more directly downward, reducing the lateral thrust. They understood that by increasing the height of a vault in relation to its width, they could further control how the forces behaved. This knowledge was encoded in their templates, their full-scale drawings on tracing floors, and in the very shapes of their stone-cutting tools. They were conducting a centuries-long experiment in structural optimization, learning from every collapse, every crack, and every success, gradually refining their designs into the breathtakingly efficient skeletons that still stand today. Their buildings were their laboratories, and their legacy is a testament to the power of observational science and geometric intuition. Modern engineering has only recently caught up to the sophistication of their hidden calculations. When contemporary structural engineers began using advanced laser scanning and computer modeling to analyze these medieval buildings, they made a remarkable discovery. The principles of load distribution embedded in the stonework anticipate a fundamental modern engineering technique called finite element analysis. This is a computational method where engineers break down a complex structure into thousands, even millions, of tiny, simple elements. A computer then simulates the forces acting on each individual element to predict how the entire structure will behave under load, where stresses will concentrate, where weaknesses might form, and how the loads will ultimately travel to the ground. The knightly system of ribs, piers, and buttresses was essentially a physical, full-scale version of this. They had intuitively divided their structures into discrete, load-bearing elements. The ribs were their finite elements, and designed a network that ensured stress was distributed evenly, avoiding dangerous concentrations of force. The computer models confirmed that the paths the loads were taking through the stone were nearly optimal, achieving a balance and efficiency that we would struggle to improve upon even with our most powerful digital tools. This ancient wisdom is now directly influencing the future of our cities, particularly in the design of the very skyscrapers that define our modern skylines. The challenge for a contemporary architect designing a 100-story tower is eerily similar to that of a medieval master builder designing a soaring cathedral. How to channel the phenomenal weight of the structure, along with the added forces of wind and earthquake, safely into the earth while using materials as efficiently as possible. The knightly concept of progressive loading is the philosophical backbone of the modern super-tall building. Instead of relying on massively thick walls at the base, engineers create a tubular or diagrid system where the building's exterior is a lightweight but incredibly strong lattice that acts as a continuous, progressive load-bearing surface, channeling forces down through its entire network, much like the ribbed vault of a Gothic nave. This allows for incredibly slender, graceful towers that seem to defy their own height. The pursuit of material efficiency is no longer just an economic concern, it is an environmental imperative. Every ton of steel and concrete saved in a skyscraper represents a massive reduction in its embodied carbon footprint. By studying how the knightly orders built towering, durable structures with a minimalist use of material, we are learning to construct a more sustainable future, proving that the path to tomorrow's green architecture may very well be paved with 800-year-old stones. In the midst of a chaotic siege, with the air thick with smoke and the cacophony of battle, clear and instantaneous communication could mean the difference between a triumphant defense and a bloody defeat. The knightly orders solved this problem not by relying on runners who could be cut down or shouted orders that would be lost in the din, but by engineering the very fabric of their fortresses to become integrated defense communication networks. They transformed stone, space, and sightlines into a sophisticated information transmission system, creating buildings that were, in essence, living, breathing command and control centers. A defender didn't need to be in the same room as his commander to receive an order. The architecture itself would carry the message, ensuring that critical intelligence and instructions flowed through the fortress with the speed and precision of a modern digital network, all without a single wire or battery. The acoustic dimension of this system was particularly brilliant. We've already seen how Templar chapels manipulated sound for spiritual effect, but the same principles were applied with ruthless pragmatism in their military architecture. Specific chambers were designed to function as natural amplifiers. A guard stationed in a small, domed room at the base of a watchtower, for instance, could speak in a normal conversational tone, and his voice would be carried upward with uncanny clarity through a narrow, spiraling stone staircase to the sentries at the top, a phenomenon caused by the sound waves being channeled and focused by the smooth, curved surfaces. These were the medieval equivalent of a tube-based intercom system. Conversely, other spaces were engineered to be acoustically dead. A war council room, often located deep within the safest part of the keep, would be lined with tapestries and have a heavily beamed, irregular ceiling to absorb sound, ensuring that strategic discussions remained secret, immune to eavesdropping by spies or even by someone just outside the door. The knights had mastered the art of acoustic zoning, creating pathways for essential operational noise while silencing anything that needed to remain confidential. Perhaps even more impressive was their mastery of visual signaling, an area where architecture and landscape worked in perfect concert. The strategic placement of watchtowers was a science in itself. They were never positioned at random. They were part of a vast, interconnected web of observation. From the highest tower of one fortress, a sentry could clearly see the signal fires of the next commandery 20 miles away, which in turn could see the next, creating a relay system that could transmit a message across an entire region in a matter of hours, a breathtaking speed for the medieval world. But the true genius lay in the architectural details that made this possible. Arrow slits and observation windows were not just holes in a wall, they were precision viewfinders. Their narrow, splayed design created a fixed, optimal field of view, effectively framing the distant tower or mountain pass they were meant to monitor. This eliminated guesswork and ensured that a sentry's attention was directed exactly where it needed to be. Furthermore, the interiors of these towers were often painted white or a light color, not for decoration, but to reflect and maximize the available light, making it easier to see distant signals even at dusk or on an overcast day. The castle itself was a giant optical instrument, its windows acting as calibrated lenses to extend the reach of the human eye. This holistic integration of communication into the structural design represents a profound, early understanding of a concept that is absolutely central to modern architecture: the idea that the flow of information is as critical a utility as water or electricity. The knights recognized that a fortress was not just a collection of defensive features, but a single, complex organism that needed a nervous system to coordinate its actions. A breach at the outer wall had to be communicated instantly to the inner bailey. a shortage of arrows at the main gatehouse needed to be relayed to the central armory. The movement of enemy troops observed from one tower had to be shared with every other defensive position. By building these communication pathways directly into the stone, they created a system that was inherently resilient. It couldn't be cut like a telegraph wire. It didn't require fuel like a radio. It was always on, always active, and integral to the building's very existence. This turned their garrisons into highly coordinated, situationally aware units that could react to threats with a unity and speed that often seemed supernatural to their besiegers. Today, the architects and engineers who design our most critical modern facilities are direct students of this medieval philosophy. When you walk into the operations center of a major airport or the mission control for a space agency, you are entering a space that has been meticulously engineered for information flow, much like a Teutonic Knights command tower. The central principle is identical. Architecture must facilitate, not hinder, communication. The open, tiered layouts of these modern command centers are designed to eliminate physical barriers to visual contact, allowing a shift manager to make eye contact with a dozen different station operators simultaneously. The strategic placement of massive display screens ensures sight lines are preserved from every workstation. Acoustic treatments on the walls and ceiling are calibrated to control ambient noise, preventing the rise of a chaotic din that would make verbal communication impossible during a high-stress event. These spaces are not just rooms with computers in them. They are carefully tuned instruments for collective cognition, where the environment itself is an active participant in processing and disseminating information. The application extends powerfully into the realm of emergency response and public safety. The design of a modern fire station, for example, incorporates these very principles. The fire poles and open sleeping quarters aren't just traditions. They are engineered solutions for rapid, silent communication and mobilization. The sound of an alarm is channeled through the building in a way that wakes everyone instantly, while the open plan allows for non-verbal, visual coordination as firefighters descend and suit up. In hospital emergency departments, the layout of nursing stations, patient bays, and supply rooms is planned to minimize the steps and the shouting required during a trauma resuscitation. The goal is to create what military theorists call a shared situational awareness, where every member of a team, from the commander to the newest recruit, has a common, accurate understanding of the evolving situation. The knightly orders achieved this with stone sightlines and whispering galleries. We achieve it with fiber optics and digital displays, but the underlying human need is unchanged. Their fortresses stand as a timeless testament to the idea that the most effective organizations, whether defending a castle or managing a city-wide crisis, are those whose very environment has been designed to think and communicate as one. That philosophy of working with nature rather than dominating it reaches its ultimate expression in their 22nd feat, environmental harmony engineering. This wasn't a single technique, but an entire design ethos, a deep-seated belief that the most formidable fortress was one that was an organic extension of its landscape. The knightly architects approached a building site not as a blank slate to be conquered, but as a complex, living partner in the design process. They possessed an almost reverential understanding of local microclimates, geology, and ecology, and they harnessed these forces with a subtlety that makes our modern, energy-guzzling attempts at climate control seem brutally inefficient. Their goal was to create a seamless dialogue between the built environment and the natural world, resulting in structures that felt as though they had grown from the earth itself, offering profound comfort and resilience by collaborating with the elements, not waging war against them. Take the simple yet brilliant principle of solar orientation. Before a single foundation trench was dug, these master builders would spend entire seasons observing the sun's journey across the sky. They didn't just note where the sun rose and set, they tracked its precise, low arc in the winter and its high, blazing path in the summer. This celestial observation directly dictated the entire layout of a commandery. In the cold climates of northern Europe, a Teutonic Knights infirmary would be strategically positioned with its longest facade facing precisely south. This ensured that during the short, weak days of winter, the low-hanging sun would pour its precious warmth deep into the sick room, its rays absorbed by the dark stone floors that would slowly release the heat throughout the long, cold night. Conversely, the same building would be designed with deep, overhanging eaves or a strategically placed gallery. When the summer sun rode high in the sky, these architectural features would cast the south-facing windows into shade, passively blocking the intense heat while still allowing for ample indirect light. This was a built-in, zero-energy seasonal thermostat, a perfect collaboration with the solar cycle that required no moving parts, no fuel, and no maintenance beyond the initial, intelligent placement of the walls. This harmonious relationship extended powerfully to the invisible force of the wind. The Knights were masters of passive ventilation, engineering their buildings to breathe with the landscape. They carefully identified the direction of the prevailing winds and then designed their structures to capture and channel this natural airflow. In their Middle Eastern strongholds, like those of the Knights Hospitaller in Rhodes, this reached a high art with the construction of wind-catching towers known as malkafs. These tall, chimney-like structures rose high above the roofline, where they could capture the faster, cleaner breezes that flowed above the dust and heat of the ground. The malkaf would funnel this cool air downward, channeling it through the heart of the building. Often, this incoming air would be directed to pass over a courtyard fountain or an underground cistern, where it would be naturally cooled and humidified before flowing into the living quarters, providing a form of ancient evaporative air conditioning. The stale, warm indoor air would then be displaced and forced out through strategically placed vents on the leeward side of the building, creating a continuous, gentle, and completely passive circulation that flushed out humidity and odors, replacing them with a constant supply of fresh, cool air. This was ventilation engineered not with noisy electric fans, but with the silent, relentless power of atmospheric physics. Perhaps the most striking aspect of their environmental harmony was the use of natural landforms for defense, a practice that went far beyond simply building on a hill. A true master builder would choose a site where the very terrain became an active component of the fortress's defensive scheme. A spur of rock might be incorporated directly into the foundation of the mightiest tower, anchoring it to the bedrock and making it immune to undermining. A natural cliff face would serve as an impassable curtain wall, saving the immense labor of quarrying and laying thousands of stones. A meandering river wasn't seen as an obstacle to be bridged, but as a ready-made moat that could be easily diverted into a defensive channel. In some of the most advanced designs, the entire approach to the castle would be guided by the natural topography. The only accessible path would force an attacking army to march with a steep, defenseless hillside on one flank and a treacherous ravine on the other, all under the watchful eyes of archers on the walls. This approach transformed the landscape from a passive setting into a lethal, active participant in the castle's defense. The fortress didn't just sit in the landscape, it weaponized the landscape, turning forests, rivers, and cliffs into silent, permanent allies. Modern sustainable architecture is in many ways a global movement to rediscover this lost wisdom. The principles the Knights applied intuitively are now formalized under terms like bioclimatic design and permaculture, which seek to create buildings and settlements that work in synergy with their local environment, not in opposition to it. Contemporary architects, particularly those pursuing the highest standards of passive house certification, have returned to the fundamental practice of meticulous site analysis. They use sophisticated software to model the sun's path and the wind patterns, not to conquer them, but to invite them in as design partners, just as the Knights did through observation. The modern concept of earth sheltering, where a building is partially buried to leverage the ground's stable temperature, is a direct descendant of the knightly practice of building into hillsides. Their work demonstrates that true sustainability isn't about bolting solar panels onto an otherwise energy-hungry box. It's about designing the box itself to need as little energy as possible from the very beginning, by listening to and learning from the sun, the wind, and the land it rests upon. This philosophy offers a crucial, urgent lesson for our contemporary world, where architecture is a major contributor to global energy consumption and carbon emissions. We have spent the last century using cheap fossil fuels to overpower our local climates, building glass skyscrapers that become ovens in the summer and iceboxes in the winter, requiring massive, constant inputs of energy to make them habitable. The knightly approach presents a radically different and ultimately more resilient path. It shows us that comfort and protection do not have to come at such a high environmental cost. By re-embracing the principles of environmental harmony, by orienting our buildings to the sun, designing them to catch the wind, and integrating them respectfully with the land, we can create a built environment that is not only far more efficient but also more beautiful, more comfortable, and more deeply connected to the world around us. Their legacy is a powerful reminder that the greatest architectural feats are not those that dominate nature, but those that so skillfully collaborate with it that the line between the building and the environment gracefully and sustainably disappears. Yet the ultimate expression of the knightly engineers' foresight was their rejection of permanence in defense, a radical concept in an age defined by stone. They recognized a fundamental truth that still echoes through modern security doctrine. A fortress that cannot change is a fortress that will eventually fall. A static defense, no matter how formidable, becomes a known quantity. An enemy can study it, probe its weaknesses, and given enough time and resources, develop a specific, unstoppable counter-strategy. This understanding led to one of their most forward-thinking innovations, modular defense components. This was not about building a single, perfect defensive scheme, but about creating a flexible toolkit of interchangeable elements that could be rapidly reconfigured, turning the entire fortress into a dynamic, responsive organism capable of adapting its defensive posture to counter whatever novel threat appeared at its gates. Imagine a great gatehouse not as a fixed, immovable structure, but as a system of plug-and-play defensive units. The primary killing zone behind the main gate might be equipped with a series of heavy stone sockets set into the walls and floor. In times of conventional assault, these sockets could hold massive, prefabricated timber barricades to slow down an enemy breach. But if intelligence reported the enemy was preparing to use a battering ram or a primitive cannon, those same barricades could be quickly disassembled and replaced with angled stone baffles, designed to deflect projectiles or cause a ram to glance off harmlessly. The murder holes in the ceiling above might have interchangeable inserts, one set with narrow grates for pouring boiling liquids, and another with wider openings for dropping heavier, stone caltrops meant to shatter a ram's structure or injure the men operating it. This modularity extended to the very walls themselves. Sections of the battlements could be fitted with different types of protective screens. A standard wooden hoarding might be replaced with a heavier, metal-reinforced version if fire was a concern, or even temporarily removed to create a clearer field of fire for newly arrived archers with longer range weapons. The knights were essentially practicing a form of medieval version control, constantly updating their defensive software with new physical patches to counter the latest siegeware developed by their adversaries. This required an incredible degree of organization and foresight. A commandery would maintain a veritable warehouse of these modular components, all standardized and ready for deployment. This wasn't a chaotic scramble for materials during a crisis. It was a pre-planned, systematic approach to defense in depth. Knights and sergeants would train in the assembly and disassembly of these systems, conducting drills to ensure they could reconfigure key defensive points under the pressure of an imminent assault. This transformed the defenders from passive occupants of a static shell into active participants in an evolving defensive dialogue. They weren't just manning the walls, they were reprogramming them in real time, forcing the attackers to constantly re-evaluate their tactics and never allowing them the comfort of a fixed, predictable target. This philosophy of dynamic response is the direct intellectual ancestor of modern adaptive security architecture. Today, the designers of everything from corporate data centers to national border installations face the exact same problem the Knights did. Static defenses are obsolete almost as soon as they are built. A fixed security protocol is a puzzle that a dedicated adversary will eventually solve. The modern solution, therefore, is to build flexibility and unpredictability directly into the security system. Consider a high-security data center. Its digital perimeter isn't protected by a single, unchanging firewall. Instead, it uses adaptive security systems that can reconfigure their own defensive rules in response to an attack. If a particular type of cyber assault is detected, the system can automatically shift traffic, isolate vulnerable sectors, and deploy specialized countermeasures, all without human intervention. This is the digital equivalent of swapping out the timber barricades for stone baffles the moment the battering ram appears. On a physical level, the principles are identical. The security checkpoints at a major international airport are the modern equivalent of the modular gatehouse. The configuration of screening lanes, the types of scanners in use, and even the questioning protocols used by officers can be altered throughout the day based on evolving threat levels and intelligence reports. Barriers and vehicle blocking systems are often designed to be rapidly redeployed to create new traffic patterns and choke points in response to a specific threat, ensuring that a potential attacker can never be certain of the exact defensive layout they will face. This constant, controlled mutation of the defensive posture is the key to maintaining an edge. The knightly insight that predictability is the greatest vulnerability has become a foundational principle of contemporary security strategy. It acknowledges that the threat landscape is a living, evolving entity, and that our defenses must possess a similar capacity for growth and change. The silent stone warehouses of the medieval commandery, stocked with interchangeable defensive modules, were the birthplaces of a concept that now governs the protection of our most critical digital and physical infrastructure, proving that true security lies not in building an impenetrable wall, but in creating a system that is always one thoughtful step ahead of the next attempt to breach it. But to truly grasp the depth of their genius, we must move beyond the tangible and into the realm of the mathematical and the divine. The 24th feat, the implementation of sacred geometry, reveals that the knightly orders were not merely building structures, they were composing silent symphonies of proportion and number, embedding what they believed to be the fundamental language of creation directly into their stonework. For these warrior monks, architecture was a form of prayer, a way to manifest celestial harmony on earth. They operated on a profound belief that God had designed the universe using perfect mathematical ratios, and by replicating these ratios in their buildings, they were creating earthly mirrors of divine order. This was not a vague aesthetic preference. It was a rigorous, disciplined application of geometric principles that they believed held both spiritual power and practical virtue, resulting in spaces that were simultaneously transcendently beautiful and remarkably stable. The most famous of these principles was the golden ratio, a mathematical constant of approximately 1.618 that appears with stunning frequency throughout the natural world, from the spiral of a nautilus shell to the arrangement of leaves on a stem. The Templars and Hospitallers integrated this ratio with an almost obsessive precision. In a typical Templar chapel, you might find that the relationship between the width of the nave and its height, or the placement of a key pillar dividing the space, adheres exactly to this golden proportion. But their geometric toolkit was far more extensive. They also relied heavily on the simpler, yet equally powerful, ratios of whole numbers derived from the harmonic intervals found in music. The proportions 1:1 a perfect unison, 2:1 an octave, 3:2 a perfect fifth, and 4:3 a perfect fourth were not just pleasing to the ear. The knights believed they were pleasing to the soul, and they translated these musical harmonies into spatial ones. The ground plan of a chapter house might be laid out as a perfect square, representing the earthly and stable, while its soaring roof might be crowned with a dome, a hemisphere representing the heavens. The transition between these two forms was often mediated by an octagon, a shape symbolizing regeneration and resurrection, seen in the distinctive layouts of many Templar churches. Every arch, every window tracery, and every vault was a piece of this larger geometric puzzle, its dimensions determined not by whim but by a cosmic blueprint. The breathtaking result of this discipline was a seamless fusion of spiritual meaning with unshakable structural integrity. This is where their engineering genius becomes most apparent. The sacred ratios they were so devoted to are not merely symbolically significant, they are also inherently stable and efficient structural forms. The golden ratio, for instance, creates a rectangle that the human eye finds instinctively pleasing, but it also appears in the growth patterns of many natural structures that are optimized for strength, like the branching of trees or the spirals of sunflowers. When the knights designed a pointed arch with proportions based on the equilateral triangle or the square root of 2, they weren't just creating a symbol of aspiration toward God. They were creating an arch that channeled gravitational loads more directly downward than a rounded Roman arch, reducing the outward thrust and allowing for taller, thinner walls and larger windows. The symbolic and the practical were two expressions of the same underlying truth. A pillar designed according to sacred geometry was never just a pillar. It was a theological statement about divine order, a key to understanding the building's hidden meaning, and a supremely efficient structural component all at once. The spiritual code was safe because it was intrinsic to the building's very stability. To dismantle the symbolism, one would have to dismantle the building itself. This holistic design philosophy is something that many contemporary architects are desperately seeking to recapture. In an age often dominated by the glass box and purely utilitarian modernism, there is a growing, almost palpable hunger for buildings that possess soul, that resonate with us on a level deeper than mere function. Modern architects studying these medieval chapels are discovering that the sense of awe and peace we feel within them is not an accident or a trick of the light. It is a direct consequence of their mathematical DNA. When we walk into a space built on these harmonic proportions, our brain recognizes a hidden order, a resonance with the patterns we subconsciously observe in nature. This feeling of a space being inherently right is something that modern neuroscience is just beginning to quantify. Studies using functional magnetic resonance imaging have shown that exposure to environments with balanced, natural proportions, like those found in sacred geometry, can actually reduce stress and increase activity in areas of the brain associated with positive emotional states and spatial awareness. Our minds are literally hardwired through millennia of evolution to find comfort and safety in the same proportional systems that the knightly orders identified as divine. This has led to a fascinating new frontier in design known as neuroarchitecture, where builders are using scientific data on how the brain responds to space to create environments that actively promote human well-being. A hospital designed with these principles might use specific room proportions and ceiling heights that have been shown to lower patient blood pressure and reduce anxiety. An office building might incorporate atrium spaces with dimensions based on the golden ratio to reduce worker stress and foster creativity. The goal is to move beyond building mere shelters and toward crafting environments that are actively therapeutic, that support our cognitive and emotional health. This modern scientific pursuit is, in a very real sense, a validation of the knightly order's intuitive, faith-based approach. They may have spoken the language of theology where we now speak the language of neuroscience, but they were pointing toward the same profound truth, that the spaces we inhabit are not neutral containers. They speak to us, they shape our emotions, and they can either fray our nerves or soothe our souls. The silent stone sermons of the medieval master builders, written in the universal language of geometry, are finally finding their translation in the language of modern science, offering us a timeless blueprint for creating a world that doesn't just house our bodies, but that truly nourishes our humanity. While we marvel at the mathematical precision and psychological cunning of their designs, perhaps the most humbling legacy of the knightly builders lies not in the grandness of their concepts, but in the simple, profound endurance of their materials. We live in an era of rapid construction, where buildings are often designed with a 50-year lifespan, yet here stand their commanderies and chapels, having weathered 8 centuries of rain, frost, and sun with a stoic grace that shames our modern ephemeral architecture. This was no accident. The 25th and final feat, their mastery of long-term material durability, reveals a philosophy of building for eternity, a deep, almost symbiotic understanding of how stone, mortar, and the elements interact over vast stretches of time. Their structures were not erected to serve a single generation. They were conceived as permanent fixtures of the landscape, and every choice, from the quarry to the final protective coating, was made with the relentless passage of the centuries in mind. This journey toward permanence began deep underground, in the careful, almost ritualistic selection of stone. A master builder for the Teutonic Knights didn't simply choose the most readily available rock. He was a geologist of instinct and experience, able to read a stone's history and predict its future. He sought out dense, crystalline limestone or sandstone with a tight, interlocking grain, knowing these would resist the insidious work of water infiltration and frost damage. But his analysis went deeper. He understood how different stones would age together. In a single wall, you might find larger, harder blocks from a distant quarry used for the critical corners and foundations, while softer, more easily worked local stone filled the spaces in between. This wasn't a compromise, it was a calculated strategy. The softer stone would inevitably erode at a slightly faster rate, but this gentle weathering would create a protective, sacrificial layer, shedding water and shielding the more critical structural blocks behind it. They even paid attention to the stone's natural bedding planes, the direction it lay in the quarry. By orienting each block so it was placed in the wall in the same position it held in the ground, they ensured it would bear weight and handle moisture exactly as nature had intended, preventing spalling and delamination that occurs when stone is laid against its grain. This was a conversation with the very essence of the material, a respect for its inherent properties that modern mass production has all but forgotten. Yet the true, hidden secret to their longevity may not be the stones themselves, but the glue that holds them together, their revolutionary mortar. Modern Portland cement is a rigid, brittle binder. When it sets, it forms a hard, unyielding matrix that is stronger than many of the stones it holds. This creates a critical weakness. As temperatures fluctuate and the building settles, the stone and mortar expand and contract at different rates. Because the cement is so rigid, it cannot accommodate this movement. Instead of flexing, it transfers immense stress to the stones, causing them to crack and spall at the edges. The knightly mortar was the complete opposite. Their recipe was a sophisticated blend of lime, sand, and often secret organic additives like animal blood, cheese curds, or even volcanic ash. This created a mortar that was deliberately weaker and more flexible than the stone it bonded. It was a living, breathing material. When the building moved minutely, the lime-based mortar could compress and stretch, absorbing the energy like a cushion. It was also self-healing. If a tiny crack did form, any unset lime in the mixture would be dissolved by rainwater, flow into the fissure, and then recrystallize, seamlessly welding the crack shut. This flexible, forgiving joint acted as a network of millions of microscopic shock absorbers throughout the entire structure, allowing the building to settle, shift, and breathe as a single, resilient organism, rather than a brittle assemblage of parts fighting against each other. The final layer of their preservation strategy was a suite of ingenious protective treatments, a form of architectural skincare designed to fortify the building against its specific environmental enemies. In rain-swept regions like the Baltic, the Teutonic Knights developed and applied sophisticated water-repellent coatings. These were often natural, oil-based sealants derived from linseed or walnut, sometimes mixed with beeswax, that would be painstakingly brushed onto vulnerable upper surfaces. This treatment didn't create a hard, impermeable shell that would trap moisture behind it. Instead, it allowed the stone to breathe while causing water to bead up and roll off, dramatically reducing the saturation that leads to freeze-thaw damage. In their sun-baked Middle Eastern strongholds, the Hospitallers used a different tactic. They would often whitewash their outer walls with a lime-based wash. While this gave their fortresses a brilliant, imposing appearance, it was also a highly functional sunscreen. The white pigment reflected the intense solar radiation, preventing the stone from overheating and expanding during the day, which minimizes thermal stress and the resulting microfractures over time. They even manipulated the building's immediate microclimate, planting specific types of ivy that would provide a shading canopy in summer while dying back to allow sunlight in during the winter, and ensuring gutters and drainage channels were meticulously maintained to keep water flowing away from the foundations. Every element of the building, from its chemical skin to its relationship with the surrounding environment, was actively managed for long-term health. Modern conservation science is only now beginning to fully decode the sophistication of these medieval recipes and techniques. When restorers work on an 800-year-old Templar chapel, they often face a conundrum. Repointing the crumbling joints with modern cement mortar, a common practice in the early 20th century, has proven disastrous. The rigid cement traps moisture, accelerates the decay of the original stone, and creates a hard, unyielding crust that prevents the building from moving naturally, often leading to more severe damage than the original weathering. The solution, learned through painful trial and error, has been to return to the Knights' own formulas. Laboratories now analyze samples of the original medieval mortar, using mass spectrometers to identify its exact composition, and then work with traditional lime kilns to recreate it. This has sparked a renaissance in natural building materials, with contemporary architects and engineers recognizing that the pursuit of ultimate strength is not always the path to ultimate longevity. Sometimes resilience requires flexibility, permeability, and a willingness to work with rather than against the natural processes of aging. This forward-thinking philosophy represents sustainable thinking at its most profound and fundamental level. In our contemporary world, we speak of a building's life cycle cost, a calculation that includes not just the initial construction, but the maintenance, repair, and eventual demolition over its entire existence. The knightly orders were the undisputed masters of minimizing life cycle cost because they engineered their buildings to have a near-infinite life cycle. They built with an intergenerational responsibility that stands in stark contrast to our culture of planned obsolescence. They understood that the most sustainable building material is the one you don't have to replace, and the most eco-friendly construction process is the one that only happens once. Their legacy, etched in stone that has outlasted empires, challenges us to rethink our entire relationship with the built environment. It asks us a simple, powerful question: are we building for our time or for all time? Their silent, enduring fortresses suggest that the greatest testament to our ingenuity is not a structure that dazzles for a decade, but one that stands as a quiet, resilient guardian for 1,000 years, a gift of stability and beauty passed forward through the unending stream of generations. Looking back across these 25 astonishing engineering feats, a startling pattern begins to emerge, one that forces us to reconsider the very trajectory of human innovation. We often imagine progress as a straight line, a steady march from primitive past to sophisticated present, but the legacy of the knightly orders reveals a different story, one of rediscovery. Many of the principles we hail as revolutionary breakthroughs in contemporary architecture are, in fact, ancient solutions being dressed in new materials. The knightly engineers, working with chisel, compass, and a deep well of observational wisdom, arrived at conclusions that our own science, with all its computational power, is only now formally verifying. This isn't to diminish modern achievement, but to highlight a profound truth: the fundamental laws of physics, human psychology, and material behavior are timeless. The genius lies not in the tools you possess, but in the depth of your understanding of these immutable rules. Consider the modern revolution in sustainable design. Today, we invest millions in complex systems to achieve what the Hospitallers engineered into their infirmaries with simple stone and air. The concept of bioclimatic architecture, a term that sounds thoroughly 21st century, is precisely what they practiced. Their strategic building orientation to harness the winter sun and block the summer heat is the direct ancestor of the sophisticated solar path modeling used by architects today. Their use of thermal mass to stabilize indoor temperatures is the same principle behind modern buildings that use phase change materials in their walls to absorb and release heat. The key difference is one of mechanism, not of concept. Where we might use a computer to calculate the optimal angle for a roof overhang, they used a gnomon and years of patient observation. Where we use concrete for its thermal mass, they used locally quarried limestone. The outcome, a building that requires minimal energy to remain comfortable, is identical. Their sustainable solutions were born of necessity and a limited palette of materials, forcing an elegance and efficiency that we, with our abundance of energy and technology, often overlook in our initial designs. This parallel extends powerfully into the realm of structural engineering. The knightly mastery of progressive structural loading, of creating invisible networks of force distribution within their stonework, is the physical, full-scale precursor to our most advanced digital design tools. When a modern engineer uses finite element analysis software to design a skyscraper, she is essentially doing what the master mason of a Teutonic fortress did with geometric rules and templates. The software breaks the structure into millions of tiny elements to simulate stress. The mason broke it into ribs, piers, and buttresses. Both were seeking the same goal: to channel immense forces along the most efficient paths, creating a structure that is both strong and materially economical. The soaring, lightweight diagrid exoskeletons of contemporary towers, like London's Swiss rebuilding, are the direct conceptual descendants of the ribbed vaults and flying buttresses of a Gothic cathedral. In both cases, the structure is not hidden but expressed, and its form is a direct diagram of the forces it carries. The medieval builder just drew that diagram in stone instead of on a computer screen. Perhaps the most humbling parallels emerge in the field of security and defensive architecture. The layered defense of a concentric castle, with its killing zones and psychological warfare, is the medieval blueprint for modern defense in-depth strategies used to protect everything from corporate networks to national borders. The Templars' understanding that a defense must be dynamic, leading to their modular defense components, is mirrored in today's adaptive cybersecurity that reconfigures its digital walls in response to an attack. Their use of camouflage and concealment to create ambiguity is the same principle behind modern military stealth technology and the unmarked, bland facades of sensitive government facilities. They intuitively grasped that the highest form of security operates on the psychological plane, creating doubt and fear in the mind of the adversary. Modern security consultants now formally study these principles of target hardening and perception management, often unaware that they are analyzing strategies perfected in the siege warfare of the 13th century. The weapons have changed from trebuchets to phishing emails, but the battle for the mind remains the same. The most significant difference, then, is not in the intellectual leap, but in the tools of execution. The knightly orders worked with a slow tech that demanded foresight and patience. A mistake in their calculations might take years or even a generation to reveal itself in a catastrophic collapse. This enforced a culture of meticulous care and intergenerational responsibility. We, by contrast, live in an age of fast tech. We can model a building in a week, erect it in a year, and often we see its failures within a decade. Our reliance on industrially produced materials like steel and concrete has given us incredible speed and scale, but it has also disconnected us from the intimate, hands-on understanding of material properties that the medieval mason possessed. He knew his stone personally, its grain, its strengths, its quirks. We specify concrete of a certain grade from a catalogue. This disconnect can sometimes lead to a fragility masked by apparent strength, a focus on immediate results over long-term resilience. Ultimately, this comparative analysis offers us a crucial lesson in humility and inspiration. It humbles us by showing that our assumed technological superiority is, in many fundamental ways, a rediscovery of ancient wisdom. But it also inspires us by demonstrating that human ingenuity is a constant, capable of breathtaking achievements regardless of the technological context. The knightly engineers were not primitive. They were pioneers working at the absolute limits of their era's knowledge and materials. Their legacy challenges us to look beyond the shiny allure of new technology and return to a deeper, more profound kind of innovation, one based on a holistic understanding of nature, a respect for materials, and a design philosophy that prioritizes longevity, efficiency, and harmony with the human spirit and the natural world. They built for eternity, and in doing so, they left behind not just ruins, but a timeless blueprint for what it means to build wisely. The legacy of these 25 hidden engineering feats is far more than a collection of clever medieval tricks. it is a living, breathing school of thought carved in stone. The concentric castles, the whispering chapels, the self-sufficient commanderies, they are not relics of a bygone era, but active participants in a conversation that spans 8 centuries. They stand as a powerful counter-argument to our modern obsession with technological complexity, reminding us that the most profound solutions often emerge not from an abundance of resources, but from a scarcity that forces deep, creative thinking. The knightly orders, constrained by the limits of their time, were pushed to uncover the very essence of architectural principles, stripping away the non-essential to reveal the elegant, underlying truths of physics, psychology, and environmental harmony. Their work demonstrates that true innovation isn't about having the most advanced tools, it's about having the deepest understanding of the problem you are trying to solve. This legacy speaks directly to the great challenges of our own century, as we grapple with a climate crisis driven by energy-intensive construction. The passive temperature regulation and sustainable resource management of the Hospitallers offer a masterclass in low-carbon living. Their buildings were net zero by design centuries before the term was coined, achieving comfort through intelligence rather than consumption. In an age of increasing urban density and social fragmentation, their holistic design philosophy, where a single space served defensive, practical, and spiritual purposes, shows us how to build more with less, creating multifunctional, efficient environments that foster community and resilience. And in a world facing complex security threats, from cyber attacks to physical terrorism, their layered defense strategies and psychological warfare architecture provide timeless lessons in creating security that is adaptive, intelligent, and rooted in an understanding of human behavior. The Knights didn't just build walls, they built systems that thought, reacted, and communicated, a model that is more relevant than ever for protecting our digital and physical infrastructures. Perhaps the most enduring lesson is one of perspective. We live in an age of specialization where an architect, an engineer, an acoustic consultant, and a sustainability expert might all work in separate silos, their efforts later stitched together, sometimes awkwardly, into a final design. The medieval master builder was all these people at once. He was a generalist genius who held the entire, complex system in his mind, understanding how a change in the foundation would affect the acoustics of the chapel, or how the placement of a window was simultaneously a tactical decision, a spiritual statement, and a component of the building's climate control. This integrated, systemic thinking is the greatest gift their legacy offers us. It challenges us to break down the walls between our own disciplines, to foster a new generation of designers who see buildings not as collections of parts, but as unified, living systems where every element is connected and every choice has multiple cascading consequences. The true feat wasn't the vaulted ceiling or the hidden water conduit alone. It was the mind that could conceive of them as parts of a single, coherent whole. So the next time your gaze falls upon an ancient fortress silhouetted against the sky, or you step into the cool, silent vastness of a medieval chapel, look closer. You are not just seeing a monument to faith or power. You are standing before a library of engineering wisdom, its shelves made of stone and its pages written in light and shadow. See the curve of the vault not just as an arch, but as a calculated path for gravitational loads. See the narrow arrow slit not just as a weapon port, but as a carefully designed viewfinder and a glare control device. See the entire structure not as a static object, but as a dynamic participant in a dialogue with the sun, the wind, and the land itself. These structures have endured not in spite of their age, but because of their intelligence. They are a testament to the power of the human mind to uncover the deep patterns of the natural world, and to weave them into a built environment that is not only strong and beautiful, but wise. Their silent, enduring presence is a question posed to our own time. Are we building for the moment or for the ages? The stones of the knightly orders, having weathered a millennium, suggest that the answer lies not in the complexity of our tools, but in the depth of our understanding and the wisdom of our intent.